Let's be honest, most Node tutorials are simply not cutting it. They're either way too short or they focus on too much surface level BS if I'm being real. How do I know? Because I've been in your shoes before trying to learn Node myself, and I spent so much time on crappy tutorials. It sucked and was really stressful, especially when trying to learn a knowledge-packed topic like Node.js. You're simply not going to learn it in 30 minutes or even an hour. It's going to take time. But don't you worry, because I can guarantee you that this crash course is what you've been looking for. Pretty confident? Let me give you a couple reasons why. Reason 1, you get to learn from Adam, who has been a backend lead for nearly a decade and has helped build backend systems for billion-dollar companies. He's even worked on the Tesla Powerwall. Crazy, I know. Reason 2, this crash course doesn't just teach you basic Node.js principles. It teaches you advanced topics that you need to know to become a professional backend developer. Topics like internals, module systems, NPM package management, plus expert tips, tricks, and advice that you can only get from someone like Adam, who has years of experience in the industry. Reason 3, this crash course doesn't just teach you theory. You'll get to put your new skills to the test by building a planet finder project, which we'll use to find habitable planets for the human race. That's right, this is a legit real-world project, not another boring task manager application. Reason 4, this crash course you're about to watch is part of Adam's complete Node.js Developer Bootcamp course, which is one of the most in-depth courses for Node online, with over 46 hours of video time alone. Trust me when I say it goes over everything. Plus, you get to build real-world projects that actually give you the confidence to build your own projects and stand out from other candidates. His bootcamp has taken people from complete beginners to senior backend developers. So if you like this crash course and want to keep diving deeper, we highly recommend checking that out. From personal experience, you won't regret it. Enough chit-chat from me. Let me hand it over to Adam so you can start becoming a Node.js master. Enjoy!
Hello! All right, now before we dive into the code, before we start building Node applications, we need to talk about how Node was born. But in order to talk about how Node got started, why it's so big, why it's everywhere, and why you need to learn it, well, we need to ask this question. How do you run JavaScript? Pause and think about this. How do you run JavaScript? If I told you, hey, run this piece of JavaScript code for me, how would you do it? Would you be able to run JavaScript on any computer? Let's say you bought a brand new computer. Can you run JavaScript on it? Well, for some of you, your first answer might be, well, yeah, I can run it in the browser. If we go to our browser, let's say you're using Google Chrome, Firefox, whatever. You can open up the developer tools and you can run JavaScript in your console, right? But the thing that's running JavaScript for you here is not your computer. I mean, yes, it's your computer, but it's the browser that you downloaded or came pre-installed on your computer when you bought it that allows us to run JavaScript. If we had a fresh computer with nothing installed, well, JavaScript would be meaningless to the computer, right? I mean, that's what programming is. Programming, such as using a programming language like JavaScript, is us, as programmers, writing instructions so that a computer, a machine, follows those instructions. And the way a browser, or we're able to run JavaScript, is by writing JavaScript, and then we feed it into something like this. Now, what this is in this 8, well, we call that a JavaScript engine. We're going to get back to that shortly. But we essentially write instructions so that our machines do something with those instructions. In our case, maybe have interactivity on a website. But in order for us to be able to run JavaScript, we need this thing right here. We need a way for a computer to understand JavaScript. And this is what a JavaScript engine does. When we download, let's say, Google Chrome, it comes in with a built-in JavaScript engine. This JavaScript engine takes whatever we write over here and understands it and runs the code for us. But can we run JavaScript without a browser? How would you run JavaScript outside of a browser? I mean, we just talked about how we need this piece, this JavaScript engine, in order for a computer to understand the instructions that we write. So how can we use this engine, but without a browser? Is that even possible? Well, let's do a quick Google search here. If I type in JavaScript engines, maybe I can use a JavaScript engine on my own instead of the Chrome browser one. Well, as you can see here, a JavaScript engine is a computer program that executes JavaScript code. It reads our JavaScript and it executes it. So if I open up JavaScript engines in Wikipedia, are there multiple JavaScript engines? Well, yeah, there are. For example, Google Chrome uses something called the V8 JavaScript engine. SpiderMonkey is used by the Firefox browser. And then there's other things like JavaScript Core that is the one used by Apple in its Safari browser. So there's different JavaScript engines that can read our JavaScript code. But hold on there. We didn't really answer the question, are we able to run JavaScript outside of the browser? And this is where Node comes in. But before we get into Node, we have to talk about some of the key moments that led to Node. Because these 4 key moments are what caused the world to take notice of Node. Because up until now, we know that a browser runs a JavaScript engine. But what if we don't have a browser? We wanted to run JavaScript on our computers. We need to solve that problem. Well, let's take a history lesson. 1995, that's a big year because that's the year that the Netscape browser introduced to us JavaScript. Brendan Eich, that used to work there, essentially developed a new programming language, JavaScript, that allows us to manipulate and program things on the web. Now in 1996, Netscape had a great idea. With their version 3 of their Netscape Navigator, they introduced something called Netscape Livewire, a way to create dynamic pages using server-side JavaScript. Hey, we've heard that term before. As a matter of fact, we can even see the press release when they announced it in 1996. With the release of 3.0 version Netscape web servers, Netscape Livewire is fully integrated into web servers. Blah, 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 blah. Allows us to do essentially server-side JavaScript. But you know what? Let's forget about Livewire because it was ahead of its time and it just didn't really work. Anyway, everything went along. JavaScript was on the front end, was on the browser, and then 2008 rolls around. And this was a critical period. Why? Because Google announced something new, and that was the Chrome browser. And this symbol that you see here, that you've seen before, is what was critical. It was called the V8 engine, a new JavaScript engine. You see, in 2008, it was a pivotal moment for the web. The idea of Web 2.0 started being talked about. The idea of having websites like Flickr, like Gmail, that were interactive. It showed the world that modern experiences on the web could happen. It's more than just pages, just HTML, CSS, and a little bit of JavaScript. When Chrome released their new browser, it allowed JavaScript to run really fast, really performant. It allowed users to have really good experiences on websites because it was such a good JavaScript engine. As a matter of fact, it's the reason that Chrome browsers are so popular now. But because we can now run JavaScript a lot faster on the web, and the V8 engine was so powerful, the concept that didn't really work back in 1996 with Livewire, well, a year later in 2009, Ryan Dahl created Node.js. The idea was simple. Can we take this V8 engine that runs JavaScript really, really fast on the browser and just run it outside of the browser? Because that's the question we're trying to solve, right? We started the course with how do you run JavaScript? And up until now, we can run it on the browser. But if I told you to run it on your computer without a browser, well, before Node.js, that would have been a little bit tricky. As a matter of fact, if you want, you can even go on YouTube, search for Ryan Dahl, original Node.js presentation, and still see the presentation where he released Node.js to the world in 2009. It's a really interesting talk and a bit of a history lesson. Now, Ryan Dahl had a bit of luck on his side because there were more and more JavaScript developers in the world working on web applications, but we now have the ability with Node to say, hey, can we run JavaScript outside of the browser? Maybe we can do what Python, PHP, or any other programming language can do, which is run code on things like servers. And because there were so many JavaScript developers already, Node was able to create this idea of a full stack developer. A full stack developer is somebody that can work on the web, but also in the world of, let's say, backend servers, microservices. And there you have it. Node was born in 2009, and now, well, it's a big player in the programming world. And if you see here, we see that Node.js is a JavaScript runtime built on Chrome 8's V8 JavaScript engine. All right, we know what Chrome's V8 JavaScript engine is, but what is a runtime? Let's learn about that in the next video. So we just learned what Node is, kind of. We're still working there, but the other piece of information that we need to solve is what is a JavaScript runtime? Because Node is a JavaScript runtime. It's not a programming language, it's not a framework, it's a runtime. So let's demystify that. What is a runtime? Now, this idea of a runtime, we're going to deep dive into it a little bit later in the course, so I'm just going to skim the surface. But you can think of it as a JavaScript environment. An environment that allows us to run JavaScript as well as do some extra stuff. Now, the way Node works is that it has the V8 engine, which, as we learned, makes our JavaScript code run really efficiently. And every time the Google engineers upgrade the V8 engine, which is very often, well, Node automatically gets faster and faster with each improvement in the V8 engine. So automatic performance boost just by that. But in order for it to do a lot more than just read JavaScript, it might want to do different things. Maybe read files, maybe access databases, maybe just run some things that aren't part of the V8 engine, aren't part of JavaScript. And that's where this libuv comes in. You see, Node.js in a simplified form is simply a way for us to give a JavaScript file to the Node.js runtime. It's going to go through the V8 engine, it's going to read the JavaScript, and anytime it sees something that maybe isn't part of JavaScript, it's going to communicate with this libuv library with a cool dinosaur logo. But what does it mean? Well, we can just simply Google libuv. Libuv is a multi-platform C library that provides support for asynchronous I/O based on event loops. Don't worry, we'll cover that later in the course. It's essentially a library that allows us to do some really neat features with Node.js that make it great for things like web servers, things that we're going to build throughout the course. If we actually go to the Node.js GitHub repo, which anybody can access because it's open source, and we go into the source folder, you'll actually see that at the bottom, we're going to access the README that says Node.js C++ codebase. And you can read about this if you really want to dive deep. But essentially, what Node and Ryan Dahl did was combine the V8 engine and this libuv, which is written in C++. V8 engine is written with JavaScript and C++, and he created the bindings between them so that they can communicate. So that whenever they encounter something that maybe needs asynchronous I/O, well, then we hand it over to the libuv. Now, I know this is kind of confusing, and we're going to dive deeper into this topic, but that's what Node is. A JavaScript runtime is an environment for us to run JavaScript that gives us a little bit more than just the V8 engine. Now, let me ask you another question. Is a web browser a JavaScript runtime? Pause the video and think about it. Based on what you learned, is JavaScript a runtime? Well, let's do a quick search here. Is web browser a JavaScript runtime? Wow, good sentencing on my part. All right, so we go to Stack Overflow. Looks like this person has the exact same question as us. And if we go to the answer, we see a browser contains a JavaScript engine. Hey, we know what that means. And the engine implements a JavaScript runtime, which includes call stack, heap, and event loop. Don't worry, we're going to learn about those soon. The browser also usually includes a set of APIs that augment the JavaScript runtime and make asynchronous blah, 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 blah. In a sense, yes, the web browser is a JavaScript runtime, right? If we go to our console, we can actually run code that isn't part of JavaScript. For example, console.log isn't actually part of the JavaScript specification. It's just something that the browsers allow us to do. Things like alert, well, those are very web specific. The browser implements this alert feature that we can use. And all of these are part of what we call the window object in the browser. The window object is a set of tools that the browsers give us that we can use that aren't part of JavaScript, but allow us to have multiple functionalities. So it's a JavaScript runtime. Remember, the V8 engine combined with some extra functionality. In the same sense, with Node.js, we have that functionality, except because it's not a browser, in Node.js, if you do window, you're going to get an error. In Node.js, we have something called global instead of the window. But if I do it here, I get an error because the browser doesn't know about global. Don't worry, we're going to dive into this specific thing in the next video. But before I keep talking, I want to go back to what we've learned up until now. How do you run JavaScript? Well, you need a runtime. You need some sort of an JavaScript engine and a runtime to be able to run the code. And that's what Node does. So how do you run JavaScript outside of the browser? You need to download a set of features so that your computer understands what JavaScript is, what you want to do. Node is, in a way, just a set of tools for us to write our applications. That application uses the V8 engine to read the JavaScript, and anytime there's something that requires some sort of things like worker threads, event queues, event loops, again, something we'll cover later on, well, we use the libuv library, and Ryan Dahl created these bindings for us that communicates between V8 and libuv. So that now we're able to write JavaScript, gets read by the V8 engine, and then gets sent back to libuv. But we don't have to worry about what's underneath the hood. We can just run JavaScript code. And by the way, this is exactly how it works with other programming languages as well. For example, if you wanted to run Python, my computer doesn't know what Python is. Yes, maybe it might be pre-installed on my computer when I bought it, but most likely, if I write Python and throw it to the computer is going to say, "Who are you? I don't even know what that means." So just like we will in the next couple of videos, we need to actually install Node.js so that we can download these tools to run JavaScript outside of the browser. In the same way, if I wanted to, let's say, code in Python, I'd have to go to the python.org website and then download Python, or the Python, what we call interpreter, so that my computer can read Python code. Now let's take a break here. I know we're covering a lot. Your brain might be a mush right now, but don't worry, everything's gonna fall into place bit by bit. For now, grab a cup of coffee, and I'll see you in the next one.
Hello! All right, we've just started scratching the surface of what Node.js is and what it can be used for. We know that it's a runtime for JavaScript that's built on Chrome's V8 JavaScript engine, which it uses to understand JavaScript and give instructions to the computer. But we could talk all we want about Node and what it can do for us, and without actually using it and seeing it in action, we're not going to fully understand it. So let's get Node set up on our computers and actually write our first Node program. From there, we can work backwards and see, how does it work? What's the architecture of it? Why do we use it? And really dive deep into what Node is underneath it all. If we go to the official Node.js website at nodejs.org, in our browser, we're immediately shown 2 download options for our operating system. The browser is detecting which operating system we're using and giving us the 2 best options. We now have a choice between the LTS version and the current version. You see, Node.js has been around for quite a while, but it's still changing. It's still being updated and getting better. If you wanted to stay with the latest, greatest features and updates, with a slightly larger risk of more bugs and instability, you can go for the current active version here, whatever it is when you're watching this video. But you can see that the recommended version for most users over here is the LTS, or long-term support version of Node. This means that the Node developers are guaranteeing that they will maintain and support this version of Node for longer than the active version. So if we're working with real-life production systems, we want the extra stability and guarantees that we get with a long-term support version. And because of that, for this course, I recommend this LTS version right here. We can also go to the downloads page and see that there are plenty of options here to install Node for every operating system. There's installers for Windows and Mac OS. There's Linux binaries and an option to install from source code. If instead you prefer installing Node using a package manager or an installer for your operating system that allows you to install packages like Node, you can scroll down to the Installing Node.js via Package Manager option, which has instructions for pretty much any distribution of Linux you can think of, as well as alternative options for Mac OS and Windows. For example, using Homebrew for Mac OS, or using a package manager like Chocolatey or Scoop for Windows over here. Finally, there's this option over here to install using NVM, or the Node Version Manager, which is a program that allows you to have multiple versions of Node installed at the same time and switch back and forth between them. This is for when you're working at a large company with multiple teams using different development environments that you need to switch back and forth from. So there's plenty of options, but the simplest way and the way that I recommend is to download the LTS installer for your operating system. And since I'm on a Mac, I'm going to download the macOS installer and then open it. Now I can follow through the steps of the installer, agreeing to the license. And I might need to put in my password to give it permission to install. All right, there we go. We've installed Node. That's awesome. Now I'm going to open up our terminal. If you're on Windows, you might want to use PowerShell. And if you're on Mac or Linux, your default terminal is all you need. Because we've installed Node, we can now type in the node command, and we can pass in this -- version flag after the node command, or node-v for short. And if the version of Node that we get back that's been installed on our system matches the version that we selected from the website, we're good to go. We can also run Node without the version flag and type in some JavaScript code, like 2+2 or woo plus who, and it will be executed by the Node.js runtime. Now we could exit from Node by typing .exit and pressing enter, or by pressing Ctrl+C twice, which will put us back into our terminal. Awesome. So let's get Node installed and start diving into the fun stuff. I'll see you in the next video. If I'm on Windows, the process to install Node is luckily just as easy. Going to the official Node.js website, my version of Windows is automatically detected, and I'm presented with the latest long-term support and current versions of Node, whatever those currently are. So I'm going to go ahead and download the latest long-term support version, which is recommended for most users, and I'm going to save that to my machine. When the download is done, I'm going to run the installer. And I can click through the various steps, accepting the license agreement. And when I reach the custom setup screen, we want to make sure that all of the options here are selected, particularly the adding to the path option here, which will make sure that when we go to our terminal in PowerShell or command prompt, that we can run that node command. Usually the default settings here will have all of the options selected, so we can click Next. And here we have the optional choice to install some additional tools, such as Python and Visual Studio Build tools, which can help us when installing certain third-party modules. So feel free to select that. Just keep in mind that it will require a significant amount of disk space on your hard drive. So I'm going to click Next, and we're ready to start the installation process, where we may need to allow the Node.js installer to make changes to our computer. Awesome, the installer succeeded, so I can click Finish, and now I'm going to open up PowerShell by typing PowerShell here. And I can type my commands in here. So to make sure that the correct version of Node was installed, we'll run the node command, passing in the -v flag, and we can see that the LTS version that I selected was installed, which means that we can now run the what's called the node REPL and start typing JavaScript code. Let drink equal T. There you go. We have Node installed on our system. We'll explore this node REPL, what REPL means, and start writing some Node code in the coming videos. I'll see you then. Let's talk a little bit about the version of Node that we just installed. The Node team always gives us two main versions or variants of the Node runtime that we can download and run from the official Node page. The Node developers always maintain a latest current version of Node, as well as a latest long-term support version of Node, or an LTS version. So why do we need this LTS version? Isn't it always better to have the very latest version of Node with the latest features, bug fixes, and performance increases? Well, the truth is, oftentimes new features introduce new bugs and other changes that can break our existing code. The stability of long-term support allows developers time to create stable versions of their code when necessary, such as for production software, where an update to Node that breaks your code could cost you or the company where you work significant time and money. If we go to the About tab on the Node.js site, under Releases, we can find a chart of the scheduled Node releases. This is the plan, the development cycle for every version of Node going forward into the future. It's updated as new versions of Node are released. All of the even-numbered versions of Node currently are or will eventually become an LTS version, while odd-numbered versions will only ever be current versions. They'll never have those extra stability guarantees that LTS versions give us. So what guarantees do LTS versions give us? Well, each LTS version is separated into an active phase and a maintenance phase. When active, most changes are accepted, as long as they don't break existing code. Later, when an LTS version gets promoted to maintenance, only important bug fixes and security updates will make it into updates for that version. And if you're more okay with issues and just want the latest, greatest features, the latest current version should be okay for you. Just a little tip on how I decide which version to use. If I know I'll be deploying an application to production within a few weeks or months, I'll go with the even-numbered LTS versions. This gives me extra confidence that my code won't break when I update my Node runtime to get the latest security updates and bug fixes. On the other hand, if I'm writing code that won't be deployed to production for, say, a year, by which time I know that there's going to be a new LTS version released, I'll often go with the current latest version of Node so that when I do update to the LTS version, once it's released, that upgrade will go a little bit smoother. It'll be a little bit easier because there have been fewer changes between the current version and the new active LTS version. That's about it. All right, I'll see you in the next video. So what happens when I run the Node program inside of the terminal? I'm now running Node, and everything I type, so hello, is treated as JavaScript code. In this case, as a variable that hasn't been defined yet, which causes Node to give us this reference error. When we run Node and don't type anything after it, not passing in any arguments, we're running Node in a mode that's called the REPL. That's REPL, which stands for read, eval, print, and loop. Before we dig into that, let's think about what would happen if we typed in some code here. So say we added woo plus who. Well, in JavaScript, this would concatenate the string woo with the string who, and we get woohoo. And if we take this same code and assign it to a variable, say a constant called cheer, that variable is now assigned the value of this computation. So now if we type cheer, cheer has been assigned to woohoo. So what exactly is going on here? When we run Node and we're in our REPL, we can type in JavaScript code like our cheer. And the REPL responds to this input in some way. It responds to it by reading the input, that's the R in REPL, evaluating it, printing the result of running that computation, of running that JavaScript code, and then loops all over again. So first we perform all of these actions in sequence, and then we loop back to the start, where our REPL environment will be ready to read in the next line of JavaScript. And this will continue until we exit the program with our Control-C key combination, or we type .exit and press enter. So what exactly does the read step here do? It includes reading in our code that we type with the keyboard, but also parsing that code. Parsing means that the V8 JavaScript engine will break down our line of code and understand the role of all the different parts of it. So for example, it will understand that we have woo here as a string and who as another string. We have this plus sign where they're being concatenated. We have an equals sign where the result of this, whatever that is, and it hasn't been evaluated yet, but the parser will now know that this equal sign means that the left side here is being assigned whatever is on the right side. This parsed code will then be run and evaluated by V8, which will give us the result of this line. So it will add these two strings and assign them to the cheer constant. And finally, the result will be printed to the console in our terminal. So when we concatenated our strings, we added them together, and the result of that expression was printed in our REPL. Now, when we defined our constant, we got back undefined, because when we assign a constant, nothing is returned in JavaScript. It's only once we print our variable that we get the value of our string. Woohoo! All right. So it's worth noting that when we're typing code into our REPL, the code that we wrote earlier sticks around. So we could now type cheer, and we would always get back woohoo. I could create another constant, greeting equals hello, and I could call that. But if I try to redeclare cheer, say by creating another variable and setting it to yippee, I get a syntax error, which is JavaScript telling me that cheer was already declared. So we could continue building up larger programs using the building blocks that we've already created. But if we close our REPL and then reopen it, we lose track of what we were doing. REPLs tend to be good for quick testing of little bits of code in isolation and experimenting with how Node behaves. For example, if we're curious what happens when we try to add a number to a string, we could test that out in our REPL. but nobody would use a REPL to write a large application. It's just not the right tool for the job. It doesn't provide a way for us to save our code or separate it into different files. It doesn't allow us to edit the code that we wrote previously. Usually, we'll be writing our code for Node applications in JavaScript files in a code editor. Let's keep building up our knowledge and find out all about how to set up our Node development environment in the next couple of videos. I'll see you then. Once we have Node installed, you might want to open up your favorite text editor to start writing some JavaScript. You can use whatever you want for this. The most popular one right now is Visual Studio Code, or VS Code. Again, you can use whatever you want for this, but if you don't have VS Code, you might want to download it for your system. Whether that's Mac, or Windows or Linux. Whatever your operating system is, you can download VS Code here. And once you've downloaded it, you can open it up and start writing our first Node file. So first thing, we're going to create a new file, and we're going to save it as hello.js. In my case, I already have a file called hello, so I'll replace it. And in the editor area here, I can start writing some Node code. And by Node code, it's just JavaScript. So I could write a function, say find meaning, just like we do in JavaScript, and I'll return 42. Now, if we want to open up our terminal and run this program, we can use the terminal in our operating system, but VS Code allows us to open up a terminal by going to the terminal option and selecting New Terminal, which gives us a terminal inside of VS Code. Now, you might prefer to have the terminal separate and not clutter up your screen here too much. And that's okay. That's a personal preference. But now we can run commands like node, which would run our REPL. But if we pass in the name of the file that we just wrote, Node will run that file for us. Okay, and since our function didn't actually do anything, it looks like it's working. So let's just make sure by console.logging the result of find meaning. Awesome, it looks like things are working. Now, one of the great things about VS Code is that it supports a lot of different extensions for Node.js. These are add-ons that make our development life a little bit easier. And one that I like to make sure is installed is the Visual Studio IntelliCode plugin, which gives us some additional information and auto-completion items for when we're writing our code. So we can install that by pressing install. And now in our JavaScript files, if we start writing some code, the topmost element here, the first suggestion, is the one that's most likely to be relevant to your program. So in this case, I actually want to be calling a function on the object class, say object.assign. The IntelliCode plugin makes the auto-completion in VS Code a little bit more effective. And you can scroll through these plugins and select whichever ones you prefer. Say we're making containers with Docker and we want to install a plugin for that. We could do that. But that's for later in the course. And it's completely optional. Again, you can use any IDE or editor that you prefer. I just think that VS Code is great for the purposes of this course, and my recommendation if you don't already have a strong preference. It's all up to you which editor you choose. And at the end of the day, as a developer, you're going to be picking and customizing your environment however you like. The most important thing is that you're comfortable with your own environment. All right, I'll see you in the next one. All right, everyone. It's time to finally build our first Node project. It's going to be something simple and a little silly, but it's going to get us started on our journey to building some really nice applications later on in the course. Let's start. So I have my hello.js here and my terminal below, and we're going to start by creating a constant to save our mission, which is going to be to learn. And we're going to say if our mission is equal to learn, then we're going to use our console.log to say time to write some Node code. And otherwise, we're going to say console.log is whatever we put for our mission. So we're going to use the plus operator to concatenate the mission string with our question. And we're going to ask, is mission really more fun? Okay, so now we can run our hello.js. And we should see it's time to write some Node code because our mission is to learn. But we can improve our program slightly by using this ECMAScript 6 feature called template strings. And ECMAScript is just the latest standard for the JavaScript programming language. So recent versions of JavaScript have this feature where we can use strings with this backtick instead of a quote and surround our string with backticks on both sides. This allows us to insert variables directly using this $ and brace syntax. This is a little cleaner than concatenating the strings every time using that plus operator. And it's possible because Node is kept up to date with the latest versions of the V8 JavaScript engine, which is in turn kept up to date with the latest features in the ECMAScript standard. What this means is that newer versions of Node will contain the latest JavaScript language features. This is great, but up until now, all of our code here has been just JavaScript. We could copy and paste it, and in our browser, in our developer tools, we could paste our code into the JavaScript console, and we get the same output. But remember, because we're using Node, we actually get a few extra benefits. Because it's a runtime, it doesn't just run JavaScript. We get a few tools on top of that. So just like the browser here has the window object, which we can use on the browser, and it contains things like, if we scroll through it, it has functions like the alert function to show an alert window to the user. It has a window.close function. And if we scroll down to document, the window object is storing what's called the document object model that the browser uses to store things like the URL being browsed and the body of the HTML. These are all things that are not JavaScript. They're added by the browser to support the functionality that it needs. Just like we have browser functionality in the window object here on the browser, Node comes with its own API, or application programming interface, which is just a set of functions and how you use them. These Node APIs are things that are not pure JavaScript that are included in the Node runtime. Node exclusive features. They're things that make sense in Node that don't necessarily make sense to have in a browser. So let's take a look at an example in our Node REPL by typing just the Node command. You'll notice that we don't have access to the window object. Just like we discussed, it doesn't really make sense to have in Node, but we have other features like the process object and a few others that we'll talk about later. But we can scroll through here and we see that there's a whole bunch of different information about the process, which is just the Node program that's currently running here. One of the features in this Node object that I want us to take a look at right now is this argv property that we can see contains an array. And right now, it just contains the path to our Node executable. So this will be different on your system depending on where Node has been installed, and depending on which operating system you're running Node on. But it always contains that path to Node. So what's this used for? What's the purpose of having process.argv, which is how we access this? Process.argv. Well, let's explore this a little bit in our browser. If we search for Node process, the first result should be the Node.js documentation, which will default to whatever the latest version of Node is. And if that doesn't match the version of Node that we're currently using, then we can go to this dropdown and select your version of Node. And on the left here, we have a list of all of the modules, all of the APIs that are built into Node. There's quite a few, so we'll explore this a little bit more later, but the one we're interested in right now is the process module. And we can see that the process object is a global that provides information about and control over the current Node.js process. Now, don't worry, we're going to talk about what global means and explore some of the other globals in the upcoming videos. But right now, we want to learn about this argv array that we saw. And the Node documentation tells us which version of Node the feature was added in. So in this case, one of the first versions of Node that was released. It tells us what the function returns, in this case, an array of strings, and then some documentation for it. So we can see that argv returns an array containing the command line arguments passed when the Node.js process was launched. And then it tells us that the first element will always be the path of the Node process, which we already saw, and that the second element will be the path to the JavaScript file being executed, while the remaining elements will be any additional command line arguments. So with this argv array, we get the arguments that were passed into Node. Back in our editor, if I exit out of the REPL and run node hello.js, using the process module, the hello script can get access to the arguments that were passed to it. Let me show you. So instead of hard-coding mission to learn, we're going to say mission is process.argv, and we're going to select the argument at the second index. Now I can do node hello.js and pass something afterwards, say the word explore, and explore will be passed as an argument to our script. It will be passed in as argv at 0, 1, 2. It will be at the second index of our array. And now our program knows that explore is our mission, which is not equal to learn. So we get, is explore really more fun than learning? Now, I could go back to the way the code was with learn hard-coded and still pass in explore as an argument, and the code will still run. Oops, I have to save my file first. And we can see that the code still runs, but we get our old hard-coded response. This is because arguments that aren't used are just ignored. And now if I add back our argv and pass in, let's say, learn, our hello script is telling us that it's time to write some Node code. Argv at the second index is learn, which makes our mission learn, and our console.log is the first option here. For now, we've used the process.argv feature to build our first little silly Node application, but one through which we've learned a lot. I now know that I have this Node runtime with me, with which I can run code and tell my machine what to do. And Node has all of these nice things that it adds for us on top of just plain JavaScript. And all of these things that we see in the documentation here are things that we're going to explore throughout the course, up until we write a real-life application. It's going to be a good one, and we're just scratching the surface, but I hope this gets you excited, because this is just the beginning. I'll see you in the next video. Welcome back. So how is Node different than JavaScript? Well, we know that JavaScript is a programming language. And anytime you want to run some JavaScript code or a file on your computer, you send it to a JavaScript engine, like Chrome's V8, but also potentially others, like Firefox's SpiderMonkey engine, or Chakra, which was used in early versions of Microsoft's Edge browser. This engine then converts those JavaScript instructions to those that your hardware on your computer or phone understands. And it then goes ahead and follows those instructions. In many ways, as a developer, you're the boss, and it's the computer doing all the hard work. I know that programming can be hard work sometimes too. But as programmers, we get to do the fun work, giving the computer all of the higher level JavaScript instructions, while it goes ahead and deals with all of the bits and bytes. Now, this flow applies regardless of how you're running your JavaScript, whether it's Node.js or Chrome or any of the other browsers. There's always a JavaScript engine reading in your code. In fact, all of these browsers that you see here use Chrome's V8 engine. Anyway, Node.js is a way of running JavaScript instructions on your computer outside of the web browser. Node only became possible because the Chrome team from Google made the V8 engine open source. And Ryan Dahl took advantage of this release by the Chrome team and created the Node runtime around the V8 JavaScript engine. Now, Node contains a lot more than just V8, but prior to Node, JavaScript could only be run in a browser and not standalone, because browsers were the only ones who had JavaScript engines, like V8. Node was built so that we could run JavaScript anywhere, including your computer, but also your phone, or, believe it or not, even to control robots. Whenever you run JavaScript outside of the browser, chances are you're running Node. Now, there are other JS runtimes available now, like Deno, which uses the V8 engine similarly to Node.js. And there's even ways of running Node.js using other JavaScript engines. So there's a way of plugging in the Chakra engine from Microsoft to power Node.js. But these are all modern developments. Node with V8 was where it all really started, and where using JavaScript on the backend, which is something we'll get into very shortly, it's where using JavaScript on the backend became widespread. Alright, so enough with the history review. What's the difference to us as developers when running JavaScript code in Node compared to when we run it in the browser? Going into our trusty REPL, we've already seen that in Node, window, and all of the global functions that it provides in the browser are not defined. This makes sense because there's no browser or browser window that's currently running. Instead, Node has its own version called global, which, like window, has a bunch of things that we can use. For example, the process object, which we saw earlier, and the argv property that has the list of arguments that were passed into our Node program. We can access things like global.process.argv, but we don't need to import them from elsewhere. In fact, we don't even need to specify that they come from global. We can just type process.argv, and it's already in scope. Global has all of the functionality that we can use directly. Even the console.log function that we're so familiar with is actually global.console.log. And we can say hello. We don't have access to browser-specific things like window or the document object, but we do have access to some very useful Node-specific things. Let's learn more about the globals that Node gives us in the next video. I'll see you then. Let's compare for a second our browser window APIs with our Node globals. In the browser, whether we're using the V8 engine, like Chrome, or something different like Firefox or Safari, we tend to deal with different things than Node. So while we have global in Node, we have window in the browser. And in the browser, we tend to deal with HTML and browsing documents instead of processes like a Node script or a Node server that are running on your system. And so on the browser, we have things that help us interact with our browsing history and figure out our location, the current address or URL our browser is pointed to. And there's this navigator object, which gives us access to data about the browser that we're currently using. These things don't make very much sense in Node. But on the other hand, we have access to things like the arguments that were passed into our process. We have information about modules that we've loaded with code and functions that we want to reuse. And because our Node scripts run on our computer and tend to live in files, when we're running Node scripts, we can get the file name of that script. And there's also __ dir name for the directory in which your script lives. As we'll see later in the course, These things will all be very useful for us when writing Node applications. But probably the most important one is this require function here, which we'll dive really deeply into because you'll see it in just about every Node program. But for now, just know that the require function here is built into Node's globals, and it allows us to import functions and modules, many of which allow us to do things that browsers wouldn't allow us to do. For example, to read and write files on your system, and even to create a server that serves those files over the internet. Now, this is all really high level, and I promise we'll be digging into all of this in way more detail, but I just wanted to give you a breakdown of some of the more common globals that Node provides for us, and compare them to what we have in the browser. For a complete list of globals, we can go to our Node documentation here and scroll down to the globals page, where we can see all of our globals, including the dir name and file name, which we mentioned, as well as some that we haven't seen before, like the exports and the set timeout function here, which you might be familiar with from the browser. It's the equivalent of the set timeout function that we have on the window object. Just like the URL down here is the Node equivalent of the URL class that we can access in our browser console. And we can see that this URL class, if we go to the URL section here, is browser compatible. It follows this WhatWG URL standard, where WhatWG is a community including Apple and Mozilla that's responsible for many of the web standards, including HTML. And this URL class follows browser conventions to help us work with addresses like example.org. This is an example of how Node has gotten much better in recent versions at bridging the gap between code we write on the browser and code that we write in Node. We can see an example of this in how this was added relatively recently in version 10.0 in 2018. Little changes like the addition of the URL class make our life when going from front-end to back-end code, which we'll be talking about next, just a little bit easier. All right, so now that we have a better understanding of the relationship between JavaScript and Node.js, and how JavaScript in the browser differs from JavaScript in Node, let's take a quick break, and I'll see you in the next video. How is Node most often used? We can use it for scripts that do things on our computer, our local machine. For example, to read and write files. But in the majority of cases, we use Node to create servers, to build web and mobile applications that connect to databases, provide user data, and things like videos, photos, and other content. And our servers also provide security features, like allowing users to log in. In order to understand how we'll be applying what we learn in the next few videos, including when we apply it in our final project, we need to get a bit of a lesson in backend technology and how it compares to the front end. Now, if you're already familiar with working with backends from front-end development or working with backends in other runtimes and programming languages, this might be review. But we need to make sure we have our fundamentals in place. When it comes to the web and even mobile, there's usually this idea of a client and a server, the front end and the back end. The front end here is your browser or mobile phone. It's what you see on the screen as a user. The back end is what happens behind the scenes, where we tend to have things like security features, input validation, and most of our business logic, especially if it's something like intellectual property. That's core to our product, and we want to be in full control over it. For example, business logic like how Google determines the ranking of websites when you search. This top secret algorithm that's so important to how Google works. And on the back end, we tend to talk to multiple different servers, providing services that we then put together in some meaningful way for our application. Let's think about this from the top. What happens when I load a website, like google.com? I'm telling my browser here, go find google.com. And it's going to go where Google has their servers for the front page of Google. And it's going to make what we call a request and say, hey server, can you give me some data for whatever is on that page? It could be the Google logo, the header, or the search bar. The server will then send back what we call a response and say, okay, here's the data that you need to display this page. This can include static files like HTML, which is the hypertext markup language used to lay the page out and, for example, separate the logo from the search bar. We might have JavaScript, which we use to perform actions on that page. Or CSS, to provide the visual styling and appearance of that page. The language that the server uses to talk to the client and the language that the client uses to send requests for data to the server is called HTTP, or the Hypertext Transfer Protocol. HTTP is used to transfer these files from the server to the browser. And oftentimes we'll see HTTPS, which is the secure version of this protocol, where all communication between the client and server is encrypted to help keep our data secure. In case someone tries to come between us in the browser and the server to snoop on what we're saying, spy on us, and steal our data. Thankfully, most websites use the secure version of HTTP by default now to make sure our data is secure when it's being transferred over the internet. So there's nothing suspicious going on here. All right, but say we load facebook.com instead, and we have a page that's more dynamic. We might ask the server, hey, I just logged in. Can you give me the data for my user and the data for my friends? And the server is going to say, no problem, here it is. But rather than sending that data in files that are static like we saw before, it could send the data back in a number of formats. The data could be JSON or XML, or even just plain text data. Where JSON is our JavaScript object format, or JavaScript object notation, using our curly braces and key value pairs, just like in JavaScript. And an alternative format is XML, which looks a lot like HTML, where we use these pairs of tags. And for example, here in our correct version, a pair of tags can have some data. That's what the backend is for. It serves us the data that we need on the front end, on the client side, to show something useful to the user. So how are backends made? We can use any language and runtime that you want. You can use Node, but also Python or Ruby, Java, or the Go programming language. And when we write code in those languages to serve our data to the front end, we call our code backend code. Now, you might be asking, why do we need the server to send us data at all? Why don't we just keep the data in the front end and do everything there? Well, on the server, we do things that we can't or shouldn't do on the browser. Things like security, logging our users in, and input validation, where the client can send us data that we don't expect, and we need to make sure that it matches our needs. This idea of a client-server architecture that we just talked about is used by most of the web. And building out that server side is what most Node applications are built to do. Our front end is almost always written in some form of HTML, CSS, and JavaScript. But the back end can be in nearly any programming language. Node allows us developers the huge advantage of programming the back end and front end in the same language. And it provides dozens of other benefits that we're going to be talking about throughout the course. So let's get to it. I'll see you in the next video. Welcome back. Let's dig a little deeper. What does the Node.js runtime over here include beyond just the V8 engine? What do the internals of Node look like so we can better understand what's going on behind the scenes? Remember, V8 here is what lets Node run JavaScript. But there's so much more to Node than just the ability to run pure JavaScript. There's this entire environment, this entire runtime that runs outside the browser, that lets us do things that aren't part of the JavaScript programming language out of the box. If we run JavaScript code like 2+2 or concatenating two strings like woohoo, in Node, V8 will know exactly how to execute that code and give us the result on our computer. But what happens when we try to get the arguments passed to our Node process? Or when we try to read and write files on our system here? All these things that Node can do that our browser can't. For that, let's take a look inside of the Node.js runtime. We've already seen that we have the V8 engine, which is what allows us to run basic JavaScript code like 2+2. But also part of Node are our Node.js APIs, or additional functions that allow us to do things like talk to the file system to read files and make HTTP requests, or look up paths on our computer for files that we might want to read and write. And even things like the crypto functionality, which has some built-in code that allows us to make our Node programs more secure. For example, by encrypting some data for us. Now, when V8 sees some code that uses these features, it'll say, okay, I need some help to execute this. And it'll call the corresponding functionality in our Node.js APIs. Some of this is written in JavaScript, but also in lower-level languages. Languages that are more like the machine code that the hardware on your computer speaks, like C and C++. And that's where these Node.js bindings come in. These bindings are what lets your JavaScript code call functionality that's implemented in C and C++, which have things like really highly optimized and tested code to encrypt your data, or to make calls to your file system, reading and writing files regardless of which operating system you're on. So for much of their functionality, the Node APIs will call into these C++ Node.js bindings. Now, the actual implementation of some of this core functionality, like working with files or the HTTP protocol, lives in what we call Libuv, with this fantastical creature over here as its logo. Libuv and V8 are the two most important internal components of Node.js. That's because Libuv deals with input and output tasks. It's this highly optimized library of code written in the C programming language that deals with input-output tasks that Node can delegate to other parts of your operating system. This is like your boss telling you to create a 5-page report on the strengths of Node.js, where he's delegating that task to you, probably because he knows you have the time and expertise to do it. Just like that boss, what this means for Node.js is that, say you're downloading a web page, and that download request takes 30 seconds. Well, a download request is input that's asking for output for a response from the web server. So what's going to happen is we'll make a request in JavaScript using the HTTP module, a function from this HTTP Node.js API, and through the Node.js bindings, Node will pass that task on to Libuv, which will just tell your operating system, okay, here are the things that I need, say the contents of a web page, and the operating system will go off and perform those tasks. So we've delegated that task to the operating system, and our Node program, our JavaScript, doesn't have to wait around for the response. Node just says, okay, operating system, let me know when my task is complete, and I'll get right back on it as soon as I can. This is called asynchronous I/O, or asynchronous input-output. It's what Node is best at, and it's something that we're going to learn a lot more about in the next coming videos, because it's so important. Nearly all of the code that we write in Node involves some form of asynchronous I/O. This includes functionality provided by Libuv, like working with your file system and making requests over the network, over the internet. Whether you're on Windows, Mac OS, or Linux. You see, part of the challenge of working with all of these different operating systems, particularly when you're working with lower level languages like C and C++, is that each of them accomplishes the same thing differently. The way you open a file on Windows versus Mac OS is actually quite different, even though you're accomplishing the same thing at the end of the day. And that's where the beauty of Libuv shines. It abstracts away all of these specific ways of reading a file, for example, so that Node will work on any system, on any platform. It does this by implementing the functionality in Libuv and exposing it to this higher level layer, which is then translated back to our JavaScript. Using what we've just learned, we can adjust our bird's eye view of what Node does, replacing our old model with a new, more accurate model, where our JavaScript goes into this Node.js process, not just with V8, but with the additional components we just talked about, which process our input and send it back to the user to do something. All right, so we have this diagram in front of us. We've talked about things like implementation and bindings. But what exactly this means for us and how each piece connects to each other probably doesn't seem fully clear to you yet. We've been talking about the internals of Node, but let's actually apply this theory. That way we can better understand these deep internal workings of Node. For that, I'll see you in the next video. Welcome back. We've been talking about how the internals of Node are structured. Now it's time to look at the code behind Node.js. As a quick recap, we saw that our JavaScript code executed in V8 will sometimes make use of these built-in Node.js APIs. And when we call one of the functions in these APIs, they go through the Node.js bindings and handled by Libuv in some way. So let's explore exactly what's going on when our code goes through the flow we see here. The Node.js project is hosted on GitHub, and you can browse it by going to github.com/nodejs/node. What we have here is the actual code that makes up Node, that has enabled us developers to create all these amazing projects and websites. Things like Netflix and projects at NASA are powered by this source code. Isn't that cool? Because Node and its components are open source, we can actually look around this code and figure out how it works, learn why things are done the way they are, and even potentially contribute new features. If you find a crazy bug that no one else has experienced, you're able to submit a fix directly to the repository here and contribute to something that has actually changed the internet. Okay, diving in, we have a few folders in the Node.js project. The two that are most interesting to us are the lib folder and the src folder. Lib over here has the JavaScript side of our Node APIs. Each module in our Node.js documentation. Remember how we had access to all these globals and APIs that Node provides for us, like the console object, HTTP, a module to get information about our operating system and access paths on our hard drive, or to get information about the process and the arguments that were passed into Node. Each of these has a corresponding file in our lib folder. We can see that there are a few folders here, but scrolling further down, we have all of these files for each of our APIs. Console. We have the file system and HTTP, all the way down to our process. Each of these files defines the functions in our documentation that make up the Node APIs. That's the lib folder. The other folder of note is src, which is the C++ side, with our low-level Node API bindings. It's that connection between the JavaScript world and the C++ world. Let's look at an example. Say we want to open a file. We know it's part of the file system module. And if we look at the documentation, scrolling down here, we'll see a fs.open function right here. This lets us pass in a path and some additional arguments. But where does this live? What's it actually doing? How does it work on both Windows and Mac OS? Well, we can investigate in our source code. We know in the lib folder, there's going to need to be a file for our fs module, because that's the module that open is part of. So we'll go into our fs.js file here. And because it has over 2,000 lines, I'm going to do a search for the open function. And I can see that one of the results is a JavaScript function, where we can follow along with the logic. We can see that we're validating the path as the first step. And then, depending on what the arguments are, we do a few different branches. There's some different options. But the most interesting piece here is this function right here, binding.open. This is where our Node.js internal bindings come in. This function will convert the values between JavaScript in our FS module and C++ over here, allowing Node to call into that optimized lower-level C++ code. So we're calling the open function available in our bindings. We can now see the full implementation of this function by going to that src folder. And again, I have some folders here, but scrolling down all the way to node underscore, I'll have a node underscore file.cc over here, where cc is one of two most common file extensions for the C++ programming language. Just like we have .js for JavaScript and .py for Python. The other extension you might see for C++ is .cpp, while the H file has the headers. Usually we'll want to look into the CC file for the bulk of the code. So going into our node file.cc, we see this C++ code. And again, this file is going to have thousands of lines of code. That might look a little bit scary if you haven't done C++ before. But we don't need to know C++ to learn something from this. If I scroll all the way to the bottom of this file, and then go back up slightly, I will find this initialize function and a bunch of these set method calls. These are associating functions from JavaScript with C++ functions in this file. So remember, we were calling fs.open, which is going to call the open function with this capital O in this file. So I'll do a search for that. And one of the results is the C++ implementation of our open function. Check it out. We can look through this code and see that it's doing some validation on our arguments. But the interesting bit here is we'll see this uv_fs_open being referenced in an async call and also in a sync call. This uv_fs_open is actually a function inside of libuv that we're saying can be asynchronous or synchronous. And exactly what the difference is between synchronous and asynchronous calls is actually a really interesting topic that we'll be going into as well. But what we can learn from this example here is that things that start with uv_ are references to libuv. And if I do a search for that in this file, you can see there's quite a few places that libuv is being used. All right. This is getting a bit deep. How far does the rabbit hole go? Where is our open functionality actually implemented? Let's complete this deep dive into the internals of Node by going all the way into the libuv source code. After this, you'll be able to say you went from the highest level JavaScript to the lowest level internal workings of Node. This is something to be proud of. Not many people can say they've done this. So on that note, I'll see you in the next video. Welcome back. Let's complete this deep dive into the internals of Node by going all the way into the libuv source code. We're about to venture somewhere that very few Node developers ever go. So we're going to have that extra advantage when it comes to knowing exactly what Node is doing. So let's get into it. In our browser, we can go to libuv.org, the official site of our favorite library over here. While libuv is part of Node, it's also meaningful on its own. Remember, Node allows us to use libuv by connecting to it with the Node.js bindings, which allow the functionality in libuv to be used by our JavaScript. But other programming languages have bindings to libuv as well. We can see this if we go to this documentation tab and follow this others link here. We can see, scrolling down all the way to the bottom here under bindings, that libuv has bindings to Ruby, Lua, C++, and Python, and all of these other common and less common programming languages. These are all client languages that can use the libuv library, just like Node. This is why it has its own website, which you can see is made with love by the libuv team. Node is libuv with a very well-known client language. That's JavaScript. But as we just saw, libuv has bindings to other languages as well. So the libuv code lives in a slightly different place, in a different repository. And let's just get into it. Show me the libuv code. We're taken to GitHub under the libuv organization. And again, we have a few folders that we can explore, containing our documentation and tests. But the bulk of the C code that makes up libuv is in this source folder. Now remember, we're exploring what happens from the JavaScript to our final result when we run fs.open to open a file. We've seen the call through the Node.js APIs in our fs.js file and going through the Node.js bindings. Now let's find it in libuv. Now, in our source folder, we can see that there are two main folders. One for Unix, which is a family of operating systems that includes both Linux and macOS, where things tend to work in similar ways. This is because both Linux and macOS are descendants of this original Unix operating system. Windows is also a family or a group of operating systems where things tend to work similarly. There are incremental updates with each version, but many of the fundamentals remain the same. So it makes sense to group these together. Let's start by looking at the implementation of fs.open on Unix. Scrolling down in the folder, we can see references to Unix systems like Android, which is Linux-based, and Darwin, which refers to macOS. Darwin is the code name for the core components of the Apple operating systems. So we're on the right track, but the open functionality is going to be in this fs.c file. Notice that unlike the Node API bindings, libuv is using C rather than C++ with its .cc file extension. Going into our file, we see that we have another few thousand lines of code. And we scroll down, we can see that this is C code, which might not really mean anything to us. But remember, the API bindings, we're calling this function inside of libuv, and we can do a search for that function, which, if you remember, was called uv underscore because it's in libuv, and then fs underscore open. This function is being called in a few places, but let's look for the definition. So our result over here is this C function definition. But this doesn't seem to be doing any opening of files. It's just really calling this init and passing in open. This is a way of calling functions that Libuv uses, but the good news is that we don't have to search far for the actual implementation. The actual implementation is in this function called uv underscore underscore fs underscore open. All right, here we go. This is where the hard work of actually opening the file and calling down into the operating system and doing file system operations is done. When we call this open function here, this is the actual open function for Unix operating systems. That makes a system call down into your operating system to do whatever it needs and then give you a handle on that file, a way of working with that file and reading and writing to it. That's the R that we get back from this function call. And it's transformed and returned all the way back up into our JavaScript. Wait a second. Let's go to our Windows version now. So we want to go back out of our Unix folder and into our Win folder, where we're going to have another fs.c file. Notice there's fewer files here for other variants of Windows because Windows operating systems are all relatively similar. There's not as much variation as between Android mobile phones and Mac OS on Apple computers, and these open source distributions of Linux that there's hundreds of. So Windows is simpler in some way, but let's see what this fs.c file has in store for us. Now remember, we're still looking for uv underscore fs underscore open. That's what's being called from our Node.js API bindings. And again, we have this init pattern, where the actual function that opens the file lives close by. And we can find it by doing a search for other functions that look like open. So we just saw one. And then the second one is this fs underscore underscore open function. This is where the good stuff happens on Windows. And we see these D words, which are structures that Windows uses. Scrolling down, we can see that this function is actually a fair bit longer than the Unix one. It's actually well over 100 lines of code, maybe 200 or 300. And we only get to the actual call that opens the file on Windows all the way down here. This create file W function gives us that file handle that we just talked about on Windows. And there's more after that. This open underscore OSF handle function over here transfers ownership of the file handle that we got from create file W to this fd variable here, or our file descriptor, which is what we then use in C to work directly on the file. And finally, at the bottom of this super long function, we set a result with that file descriptor and return it back up through our code. So why is this function so much longer than the Unix version? Well, for one, things are just a little bit more involved in Windows land. But there's also a bit of code here near the beginning of our function that allows the results of opening a file to be compatible between Windows and Unix so that we can work with files in the same way, regardless of which operating system we're on. This is one of the benefits that working with Libuv gives us as Node developers. Okay, so maybe you've been following along so far, but now you're wondering, will I need to know C and C++ for this course to be a Node developer? The answer to that is a resounding no. The whole reason why we have high-level languages like JavaScript and runtimes like Node is so we don't have to write code in these low-level languages and worry about all of these complications that you've had a taste for here. But as we learn more about what Node does, having this knowledge will allow us to be not quite as intimidated by the internals. We've now explored this code as far as we can. Any deeper and we'd have to start looking at the C libraries and the operating system code for Windows and Linux, for example. Now we can point out how things are implemented in the underlying Node source code. This is where our fs.open function call journey ends. We did it. Going this deep is not something that many people can do, so consider yourself ahead of the game. Let's take a well-deserved break, and I'll see you in the next one. Bye-bye. All right, that was quite the journey into Node's deep internals. Now that we've come up from our deep dive and are back on land, we're going to take things step by step. For the first step, let's get one definition straight. Throughout the course, and especially in this section, you'll hear the term asynchronous come up again and again. What does asynchronous mean? In programming, asynchronous is often described as the opposite of synchronous, where synchronous means code that runs line by line in sequence. So asynchronous code is code that doesn't necessarily run line by line. Let's put aside programming for a second and look at an example. Say we have a list of things that we want to do, some goals that we want to achieve on our way to being the best developer we can be. Maybe we want to start by learning HTML, and our plan is to then learn JavaScript and move on to Node, eventually getting hired at our dream job. If we're doing things synchronously, what we'll do is we'll learn HTML as best as we can, and only after learning everything we think we can possibly learn and ticking that box off, do we start learning JavaScript. And when we think we've become the best possible JavaScript developer we could possibly become, we check that off and move on to Node. And so on until we achieve that goal of getting hired. This is a synchronous way of completing our tasks. We go through our goals one by one and only move on to the next goal when we're completely done with the previous one. In contrast to this, with the asynchronous approach, we could learn HTML really, really well, as best as we can, and then we start learning JavaScript. At some point, we decide we're comfortable enough with JavaScript as a language and move on to Node. But then, along the way, we work really, really hard, have some job interviews, And hey, we get that job that we've always been dreaming about. But we're still learning JavaScript and getting better. And we're still learning Node. These are skills that we constantly improve even after we've gotten hired. I know I'm still learning even after working with Node for years and years. In real life, we tend to achieve our goals asynchronously. We're getting better at Node, but while we're doing that, we're also getting better at JavaScript. Well, code works in the same way. For most tasks in our programs, it's possible for our computers, our machines, to work on multiple tasks at the same time. When one piece of code is still executing, but your program is already moving on to the next piece of code, that's asynchronous code. Oftentimes in your programs, there will be some asynchronous functions. These asynchronous functions run in the background while your JavaScript has already moved on to the next line of code. This can be super useful because, for example, if your program is a web browser and it needs to spend some time loading a page, maybe my search results, to find out more about the Pacific Ocean. We want the browser to do that in the background, don't we? We want our browser to still be able to handle our button clicks and to let us load other web pages, even if something is loading in the background. Maybe I'm searching for images of mountains. Asynchronous programming is what allows us to do all this, handling many things side by side. And that's something that Node.js is really good at. We'll keep learning in the next video. I'll see you soon. Hello again. Let's get something straight. Something that's important for the rest of this course, the rest of our careers as Node developers, and even as JavaScript developers as a whole. What could be so important? Well, it's this part here. That Node.js is an asynchronous, event-driven JavaScript runtime. We've been hearing about how Node is asynchronous and that it's really good at working with asynchronous tasks. So what exactly are we talking about here? Let's find out. To demonstrate, let's set up a race in this race.js file. So we're going to see who's quicker. Going into my emoji database over here, we're going to have this rabbit taking part in our race. So we're going to say console.log and have the rabbit finishing. And the little rabbit is going to be racing against this slow turtle over here. So we're going to have the turtle finishing right after the rabbit. This is what we call synchronous code, where synchronous just means that the code executes line by line in order, waiting for the previous line to finish before moving on to the next. So the output of this program should be fairly easy to predict. If we pass in race.js to Node, we get, oops, I'm running the file from the wrong folder here, so I need to change directory in my terminal here to my desktop. And now I can run node race.js and hopefully see my predictable output, where the rabbit finishes first because her line of code here came first. Okay, I hear you saying that this is really basic stuff. So let's compare this with the asynchronous approach. You might remember a function from our Node globals, or maybe even from the browser and the window object called setTimeout. This function allows us to set a piece of code to be run at a later time. And the way we do that is by passing a function as the first argument here. So we can use this anonymous function using our arrow syntax, or we could use our function keyword here. That would work just as well. And have the rabbit finishing inside of that function. So this function represents what's going to execute. And the second argument is the timeout. So that's how long Node will wait before attempting to execute this function. So let's just say 1,000 milliseconds or 1 second. Our line of code here is now asynchronous. And the function that we're passing in to be executed at a later time is called a callback function. Callbacks allow us to say, when you're done doing all of this work, call me back and run my code. These callbacks are executed when some event occurs. With setTimeout, it's just after waiting for a certain amount of time. But other asynchronous functions will wait for a file to be read or a request against a database to complete. Maybe a user is logging in. All of these things that can take some time to complete that we'd otherwise be waiting around for. This is why callback functions are at the foundation of Node. They allow us to build web servers that can handle thousands of requests all at the same time without waiting for the previous one to complete first. So can you predict the output of running this program? Maybe after our discussion, it seems obvious to you. But we've just introduced a really powerful concept. Now the slow little turtle here finishes before the rabbit, even though the code for the rabbit finishing came first. This out-of-order execution is something that can take some getting used to. Our code is still running line by line, but it doesn't pause for the asynchronous function. Instead, setTimeout immediately returns, our turtle finishes, and then at a later time, after this timer expiring in the background, our callback function is executed. This is powerful stuff, so make sure it makes sense to you because we're going to be seeing a lot more of these asynchronous functions and callbacks throughout the course. And we don't want to get caught off guard by a slow turtle winning the race unexpectedly. On that note, I'll see you in the next video. Welcome back. What is a non-blocking function? Well, blocking code executes synchronously. Both Node and your browser have a built-in JSON.stringify function that blocks until completion. And any commands after it only execute once it's done doing what it does, which is that it takes a JavaScript object and returns the string representation of that object, telling us that food is love. But our non-blocking functions, like setTimeout, execute in the background or even in parallel with the rest of our code. The 1 second timer is running while the next line of code is already executing. And the myFunction callback might run in parallel with another piece of code. Like, for example, making a request to google.com. When we have some code like our setTimeout, or we're making a request, or even reading a file on our computer, you might think that your computer, your CPU, which is what is running your JavaScript code, is working really hard to read that file or to make that request against Google servers. This is not the truth. Your CPU is deceiving you. What's actually happening is that your CPU is passing off or delegating this work to other devices on your computer, like your network card, which handles communication with other devices on the internet, or your hard disk, which is searching for that file and reading the bytes that it's composed of. While these devices are doing their hard work, your CPU is basically just waiting around or going off to do some other work. It's our non-blocking asynchronous code that allows our CPU over here to continue executing the other instructions in our JavaScript program, while we're making use of our other devices, like our hard drive. We can make more efficient use of our CPU. So what's the lesson from all this? Our stringify function might not normally take very long to complete. But imagine if setTimeout was a blocking function, or make requests. These functions that can take a very long time to complete are the ones that we want to be careful with. We want to make sure that our long-running functions that are waiting for input and output from our devices, like our hard drive, are non-blocking, allowing Node to continue executing other code, and making sure that that CPU of ours stays awake. All right, I'll see you in the next one. Here's a question for you. Based on what you've seen so far, is JavaScript synchronous or asynchronous? This is a common job interview question if you're going to get hired as a Node developer. And it's something that's key to understanding Node and JavaScript fundamentals. So consider this good practice. Think about this for a second. Is JavaScript synchronous or asynchronous? When you're ready, let's continue with this video. Okay, have you figured out the answer? Out of the box, JavaScript is a synchronous language. One statement executes after the other. However, we've seen that we can write asynchronous code, where we are able to execute a callback function in the future when something completes. What's up with that? When JavaScript is run in certain environments, like your browser or Node.js, it allows us to write asynchronous functionality. But this functionality, like setTimeout, isn't strictly part of JavaScript. It comes from our Node APIs, from our global object, or in the browser from our window object. setTimeout is clearly an asynchronous function, but it only works thanks to Libuv, thanks to functionality that is not part of the core JavaScript language. So JavaScript can behave in an asynchronous way, but it doesn't come this way out of the box. You have to manipulate it to be this way. So what is Node doing to make setTimeout and our other asynchronous functions work when JavaScript itself is a synchronous programming language? Let's learn more so that we can feel comfortable discussing this in a job interview setting. I'll see you in the next one. We've reached a big question. Is Node.js multi-threaded? chances are you're well aware that computers with more processors and processor cores are more powerful, more expensive, and generally more desirable. And the way that we take advantage of our multiple cores to run our programs faster is by using threads. But what exactly are threads? And how do they help us? Let's look back at our node diagram. What we have here is a series of internal components of the Node.js process, and how a function call like fs.open might flow through these internal components. Well, the Node.js process, like any process on your computer, represents a program being currently executed. In this case, the Node.js executable. I want to show you a diagram that will help put things together from how exactly the Node process runs on your operating system to how your CPU allows you to run code asynchronously. We start from processes. What happens when you run a process on your machine? Anything like the Chrome browser or the Node process. Well, processes are containers containing your code, which lives in the memory of that process. So we might have some code with a few functions, like a first function that calls this second function, and the second function just returns the number 42. And then below, we have this code which creates a new thread using the code from that first function, and then creates another thread using that same function. Now, this is pseudocode. It's not code in any real programming language, but it's a lot like the code that you might see in a multi-threaded programming language. Something like Java or the C++ programming language. So the idea here is to have two threads, both running the first function in parallel, asynchronously. These two lines of code here might remind you of something that we saw recently, which is the setTimeout function, right? We're passing in a function to be executed asynchronously, and we're just not passing in a timer. We're saying, hey, CPU, start this thread as soon as possible. And so what happens is when this first line of code is executed, our process creates a new thread, which also lives inside the memory for our process, and it represents a single sequence of operations. Operations like functions, and the function calls that are contained in the code of your process. This sequence of operations lives inside the call stack, which is in turn part of the thread. Like a stack of bricks, new function calls go on top of the stack, and functions that are done executing are removed from the top. So in our first thread here, we start with the first function, which is added to the top of our empty stack. And then the first function calls the second function, which gets added to the stack. And if second function made any other calls, they would be continuously added on in sequence. Now, when second function returns the value 42, the second function is removed from the top of the stack. The return value is sent back to first function, and the first function is now completed, so it's removed from the top of the stack. Now, that's if we had one thread. But remember, we're creating two threads here. So what would happen in this code is we would first create that new thread, but then we would do the same thing again. We would create a second thread with its own call stack. And these two threads would run asynchronously. So in thread 1, for example, we might go through the same flow that we saw previously. We might call first function, call second function, and so on. And then perhaps thread 2 finishes calling first function and is ready for the rest of our code for second function. Notice that the two threads don't have to be in the same place in our code, in the same state. In fact, thread 2 might even be executing a different function altogether. So it might call second function directly, or even a third unrelated function. The point is, we have processes and threads inside of them, and they share memory and code, but not call stacks. Your threads can execute side by side if you have more than one, each running part of the code of your process. And that CPU of ours can constantly switch back and forth from one thread to the other to simulate executing them in parallel. But more importantly, if we have multiple cores in our CPU, each core can be dedicated to executing one thread. This applies to all processes. Your operating system can have threads helping it run things side by side. Your code editor, like VS Code, can have threads. And even the browser you're currently watching this video on has multiple threads, helping it run smoothly. So back to our example, how does this process finish? Well, the second thread needs to complete the code that it's running. So the second function gets added to the top of the call stack. And then maybe the return value of our second function is returned back to the first function in the first thread. So it gets removed from the call stack, and that thread completes. And then the same thing happens on thread 2. The important thing to note here is that the two threads are independent of each other. In terms of executing the code, they can both be in any spot of the code depending on when they were created and how fast the operations they're executing completed. Maybe even what other threads and processes were running on your CPU. All of these things can affect which thread completes first. So threads execute side by side, allowing us to execute code asynchronously by putting it on a new thread. This sounds great, but traditionally, for your application to have threads and to take advantage of everything we've talked about in this video, the programming language that your code was written in needed to support multi-threaded programming and the creation of new threads. But the reality is that things aren't as simple as they look here. Multi-threaded programming is a difficult concept to master, especially in languages like C++ and Java, where you need to have an understanding of things like mutual exclusivity and locks. These are mechanisms to keep your code and the data inside the code synchronized between all the threads so that they can work together towards a common objective. Doing this effectively can be extremely complicated to reason about and understand, and to debug when something goes wrong. You'll run into issues like what's called a deadlock, where two threads are stuck, waiting for an action that can never actually occur. Believe it or not, avoiding deadlocks is something that experienced programmers struggle with when working with these multi-threaded programming languages. It's really not an easy job. It's a source of huge bugs in basically all multi-threaded software. And sometimes you just don't want to deal with all of this multi-threading. So that's the decision that Brandon Eich made when he created JavaScript. In JavaScript, we don't have to worry about multi-threaded programming and all those complicated concepts like deadlocks, because we can't. Traditionally, JavaScript is a single-threaded programming language. If you've already been working with JavaScript for a little while, answer me this. When's the last time you had to deal with deadlocks? Most likely, the answer to this is never. JavaScript simplifies things by only allowing one thread to execute your code at a time. So then, how is Node allowing us to open files and make HTTP requests asynchronously? Does Node introduce threads into JavaScript? Okay, using our newfound knowledge on processes and threads, let's answer the original question. Is Node.js multi-threaded? But first, let's take a quick break. I'll see you in the next video. Welcome back. Here we go. The thing that allowed Node to be so successful is the ability to run JavaScript code asynchronously. And doing this in such a way that developers like you and I could focus on our application and solving interesting problems rather than worrying about complicated multi-threading logic. We've learned that JavaScript is a single-threaded language. So if it's not threads, then how does Node allow us to execute code asynchronously? Does Node add threads to JavaScript and just do a really good job of hiding them? Well, Node executes JavaScript code, so it has to follow how the language works in being single-threaded. In Node, we have one main thread. This one thread runs the V8 engine, our JavaScript code, including the Node APIs, as well as a super important part of Libuv, which is the event loop. We'll get to the event loop in a moment, but a blocking function in any of these components will cause our JavaScript to block, halting execution of our program until that blocking function completes, which is not great. But that's not the whole story. For a complete picture, we need to take a better look at our favorite library, Libuv. We've seen that Libuv handles our input-output functionality. Specifically, Libuv handles the two main types of I/O. File system operations, like the functions in our FS module, as well as the other most common form of I/O, which is network operations. We're able to execute all of these functions asynchronously thanks to this event loop. This event loop is code in Libuv that runs our asynchronous functions and executes the corresponding callback when the result of the function is ready. In Node, anytime we call an asynchronous function from JavaScript, it gets put on that event loop. This applies to our asynchronous network and file system operations. So all of our JavaScript code is running on the main thread, and any asynchronous functions are put on the event loop, which then goes off and tells your operating system to run the asynchronous function, notifying the event loop when the result is ready. It's kind of like your boss deciding when your code executes and getting notified when the work is complete. It continually listens for new events and delegates this work that we don't want blocking our main thread. Now, where does the work that gets put on the event loop actually get completed? Who are the employees or the workers that help the event loop get things done? There are two main options. Some tasks, things that tend to involve the network, like talking to servers over the internet, are done directly in your operating system, while other tasks, like reading a file, are done in what's called the thread pool. Let me explain. Inside of Libuv, we have this pool of threads, or in other words, a group or a collection of threads, which are set up ahead of time and are available to take on work as it comes in. Remember, Libuv is written in the C programming language, which does have threads. So our thread pool takes advantage of that. The threads in our thread pool are just like the threads in our process. There's one for the main thread that's executing V8, as well as the event loop, and there's a few threads, 4 by default, that are ready and waiting in our thread pool, with each of them able to handle one task at a time. We have a limited set of these threads that are available to take on work that are reused throughout the life cycle of our Node.js program. This saves our CPU from doing the additional work of creating and destroying new threads for every task that comes in. If we run out of available threads on our thread pool, well, we just have to wait for a task to complete before our thread pool is available again. So how does everything fit together? For file system operations, which use the thread pool, Libuv would send the work to one of the threads, where it would run through what it needs to do, independently of all the other threads in our application, including the main thread, which is running our JavaScript code. So this would happen in the background, and when the operation completes, the event loop would get notified of the result, executing the corresponding callback and making sure that our application is running smoothly. But there's something worth noting. Only some operations use this thread pool. There's a common misconception, even with experienced Node developers, that all asynchronous functions are executed in the thread pool. Node actively tries to avoid this because, well, threads are more complex and use up the limited resources of our thread pool. Instead, where possible, Libuv uses the operating system directly, specifically the operating system kernel, which is the core part of the operating system that talks to the computer's hardware and has multiple threads of its own. The kernel is really good at doing these basic operations, like talking to other computers over the network, using its own capabilities. Whenever the right functionality already exists in your operating system, Libuv will just make the appropriate call, saving us from using the valuable resources of our thread pool. And so, for most asynchronous operations, we skip over this thread pool. When our operation finishes running in the operating system, the event loop will receive the signal and execute any callback functions. All of this is what allows the Node.js environment to run asynchronous code. And it's what Node adds on to what JavaScript offers as a language. The fact that Node uses JavaScript, which is a single-threaded language, may sound like a disadvantage, but it's actually one of Node's biggest strengths. It means that as a Node developer, you never have to worry about managing multiple threads, which simplifies how you write code. Node already knows who should do the work to get the job done. So as a developer, you don't have to think about it. It's only the code behind Node and the code behind your computer's operating system that internally has multiple threads and uses those threads to perform input and output tasks. It's these internals that allow Node to do its famous non-blocking I/O, that it's so famous for doing really well. And ultimately, this is what led us all here, to using Node in our applications and wanting to learn all about it. All right, until the next one, bye-bye. Welcome back. In this video, we're going to take a second, closer look at the event loop. This is one of the most important parts of the Node runtime. Why is it so important? The event loop is responsible for handling all those callback functions in your Node programs. Those callback functions which allow Node to execute code asynchronously. It's this event loop that allows your Node program to do multiple things all at once, even though JavaScript is a single-threaded language. So how exactly does the event loop work? What does it look like? When you start executing some program using the Node runtime, a piece of code starts running. This piece of code is a loop inside of Libuv. That loop is called the event loop. You guessed it. This event loop, like every event loop, is a piece of code that looks something like this. We have a while loop that runs as long as some condition is true. For the event loop, it checks if the Node process should exit, and if the process shouldn't exit, so say some flag should exit is false, our event loop calls a function to process events that have been sent to the event loop. Something like process events. So our loop checks if your code is done executing and the node process should exit. And if not, it processes all the events, all the callback functions that are called by your node program. If there's no events, the function here waits until there is one. It waits until your program triggers one of those callback functions, at which point it will execute that function, passing off any hard work to the operating system or to that thread pool. When it's done processing all the events that it currently has, it'll start all over again. That's it. This loop runs while Node is running and processes all the events happening in your Node programs. Now, the code you see here isn't exactly the event loop code that Node uses. The actual loop lives in Libuv and is implemented in the C programming language, not in JavaScript. But it follows the same logic that we see here, processing all your asynchronous callbacks until Node is ready to exit, when there's no more code for Node to run. All right, now that we're aware what an event loop looks like, there's only one piece that's missing. How does the event loop process events? What does Node's process events function do? And what kinds of events does it actually handle? Let's find out in the next video. I'll see you soon. Welcome back. We now know that the event loop is a piece of code in Libuv that processes asynchronous events. It handles our asynchronous code, going through any relevant asynchronous callback functions in a loop. Node automatically enters this loop when it starts executing your code, and it exits automatically when there are no more functions to perform. So what exactly happens when the event loop processes events? When Node executes an asynchronous function, say setTimeout or our file system function to read a file on our machine, that operation is sent off to be executed in the background. As we've learned, this operation is executed in our operating system or on the thread pool. When that operation finishes and the result is ready, Node places any callback functions that it needs to run for that operation onto a queue. Say our asynchronous operation was this setTimeout that waits for 1 second before attempting to call a callback that we're going to call callback 1. What happens is that when this timer expires, when 1 second has passed, our callback is added to this queue to be executed as soon as possible. This is true for any callback that you've set to be run when some asynchronous operation completes. These callbacks are put on something called a callback queue. This callback queue keeps track of which callbacks are ready to be executed. Any new callback functions are pushed onto the queue in this order. So another setTimeout that completes immediately after our first one would add its callback immediately after. And if we had a third operation complete with a third callback ready to execute, its callback might be added to the queue as well. So new callbacks are added in this direction from the bottom and they're removed from the queue, they're executed from the top in this order, with callback 1 being executed before callback 2. This is what's known as a first in, first out queue. The first function to be put in, callback 1, is the first to be executed, because it was the first one to be pushed into that queue. This queue is like a waiting area for our callbacks, where the oldest function, the one that's been waiting longest, will be the one to get processed by our event loop first when it has a chance. We use this queue system so that all your callback functions get a fair chance to be executed in a reasonable amount of time without interrupting each other. There we go. I've probably said callback and queue a million times in the past couple minutes, but the next video is going to be a really good one. Let's find out exactly how the event loop uses this idea of a callback queue. Oh, and by the way, you may have heard the term event queue or message queue being thrown around in the context of the event loop. These are just different names that refer to the same thing. They all refer to this idea of a queue of callbacks. All right, on to the next video. Let's continue our investigation into how the event loop processes events. We've learned that when you pass a callback into a function, like setTimeout, when that timer completes, the callback gets put on something called a callback queue, or event queue, to be executed at a later time. Now, what does the event loop do with our queue of callbacks? Well, I'll let you in on a secret. There's no one callback queue. We do have queues of callbacks that keep track of which tasks need to be run, but if you look deep into the workings of the event loop, you'll see there's actually several different queues. Each one handles a different phase of the event loop. Whoa, what's this phase idea that I just introduced? Each phase of the event loop is responsible for different types of operations. There's 4 main phases of the event loop. Each of these stages is responsible for a different category of operations that the event loop processes. There's one for timers, one for input-output events, one for setImmediate, and one for close callbacks. Each of these phases has their own queue of callbacks that are executed during that phase. A callback for setTimeout would go on the timer queue, while a callback for a file system operation, well, that's input-output, so it would go on the I/O queue, which is responsible for all asynchronous input-output operations. This I/O queue is also known as the poll queue. We'll go through each of these phases in just a second. But before we get there, we need to understand this concept of timers. There's 3 types of timers that we have in Node. You might have seen some of these. We have setTimeout, we have setInterval, and we have setImmediate. We've already seen setTimeout in action, and setInterval is very similar, except it sets a function to be executed many times repeatedly, with function calls separated by a minimum of the delay that you pass in as a parameter. Rather than executing your callback once, like setTimeout, setInterval loops that function on an interval. setImmediate is a special kind of timer. It sets the callback that you pass in to be executed as soon as possible on the event loop. In theory, this means it's going to be executed immediately. But the truth is, setImmediate isn't so immediate. We'll really see this by visualizing the different phases of the event loop. Let's find out how the event loop flows through all of its different phases. When the event loop first starts executing, on the first iteration of our loop, the first phase starts getting processed. The event loop begins by going through all of our timer callbacks. These are callbacks that were passed into setTimeout and setInterval. The event loop goes through the timer's callback queue and checks if there's any functions for it to execute. Functions for timers that have completed. Once it's processed all of the functions in the timers phase, it moves on to the next phase. We're still in the first iteration of the event loop, or what we call the first tick of the event loop, and we're now dealing with all of our input-output callbacks. This is the majority of all your callbacks in a real-life Node application. It includes things like all your network and file operations, but basically anything that doesn't fit in the other phases goes here. So if your code is done reading a file, the callback for that read operation will be pushed onto the I/O phase callback queue, and it will be executed in this phase. Next up, we have the setImmediate phase. Remember, setImmediate is a special kind of timer, like setTimeout and setInterval, that instead executes after the I/O phase. As you can see, functions passed into setImmediate actually execute after those passed into timers, like, for example, setTimeout. It's called setImmediate because it runs immediately after any I/O operations have finished executing, and before another cycle of the event loop starts. Before we move on to that next tick, there's one more phase, the close callbacks phase. This is for when you close a file or a network connection, and you have a callback that executes when that connection is closed. That's what goes in this last phase. When all of the close callbacks have been processed, the event loop cycle begins again. And it goes through this list of different functions that it needs to execute. So it first checks the timers, asking, are there any timer callback functions to execute? If yes, it runs them. And when it's done, it asks the I/O callback queue, are there any functions for me to execute? Does the callback queue for this phase have something for me to process? If not, or once it's done processing, it moves on to the next phase, and so on. until we start a new tick of that event loop. Now, there are a couple of other phases in the event loop, like the idle and prepare phase, but that's only used internally by Node. Our JavaScript can't do any operations there, so these phases aren't really important to us. The 4 phases we see here are those that really capture the behavior of the event loop and how it interacts with JavaScript. By going through all these different types of functions in the different queues, the event loop makes sure that all the functions that make up your asynchronous Node programs eventually execute. And that's it. Node combines this event loop along with the V8 engine and Libuv to bring JavaScript to the server, allowing us to create all the websites and servers and applications that we can possibly imagine. Good stuff. I'll see you in the next one. As we're learning about the internals of Node, it's worth taking a step back and considering how is what we're learning about Node different than languages like PHP and Python. We've already seen that a crucial difference with Java, C, and C++ is that those languages support multi-threaded programming. But PHP and Python are both high-level, easy-to-use, single-threaded programming languages, just like JavaScript. So what's the difference? If we think back in the day, say 20 years ago, when it came to the web, PHP and Python followed a more traditional model, where they needed a web server, something like Apache, to handle multiple requests coming in. Apache was a big hit, and it had a lot going for it, including that it was free and open source. With this web server, any request to our server, say asking for some data, was blocking. So we would handle it in a new thread. Because each thread would be blocked by our blocking PHP or Python code, we would have to spawn another thread in Apache for the next request, and the next request after that, and so on and so on. Each client talking to our server would get its own thread, which means that our server needed a lot of threads, with a lot of resources being used by those threads. The server would only be able to handle as many connections as it could threads, which made building sites that serve millions of users quite difficult and expensive. Serving a site like Facebook or Google that gets a lot of traffic, your server would crash pretty quickly. In 2009, Node became popular because of its model of non-blocking I/O that we talked about. Taking in all of these requests, in the Node.js model, we take the request into the JavaScript engine. Remember that it's mostly single-threaded. And for each request coming in, we quickly pass it off from the engine to be handled by Libuv, which queues it up on the event loop. even though your JavaScript code runs in a single thread, Node allows you to handle thousands of concurrent requests by delegating or passing off the majority of the work. It passes this work off specifically to the multiple threads in the thread pool. And wherever possible, skipping over the thread pool and talking directly to your operating system. Because your operating system is already multi-threaded, this work can be done without blocking your server. All of this happens in the Node.js process. There's no need for an additional web server, like Apache, to create thousands of threads. Looking back on things, the PHP model worked pretty well. But for many connections at the same time, Node's I/O model worked really, really well. Now, looking forward, things these days are changing, and the concept of non-blocking input-output is being used more and more. Python, for example, has integrated support for running an event loop out of the box, bringing it a step closer to Node. However, none of these languages that we've talked about make it as easy to work with asynchronous programming as JavaScript in Node. Because Node was built specifically to do asynchronous, non-blocking I/O really simply and efficiently. I know it sounds like an advertisement, but it's the truth. And we now have the tools to understand why. Just as a side note here, you can put a web server like Apache or the newer giant that's competing with Apache, Nginx, in front of a Node server. And it's actually a good idea to use them together sometimes if you have a larger, more complex application and you're going to be handling thousands of concurrent users. But it really depends on what you're building. We'll take a look at performance when we build our final project. But for now, let's dive into exactly when it's best to use Node. It's going to be a good one, so I'll see you there. Welcome back. So what is Node best at? When is using Node the right choice? Let's think about this in terms of what we've learned in this section. Remember this visual? How when your computer is reading from a file or making requests over the network, your CPU is spending a lot of time just lounging about, not working very hard. And it's your devices, like your hard drive and your network card, that are doing all of the work. We now have a more complete picture of this, where our Node code sends work to our operating system through the JavaScript engine and Libuv, and it's our operating system which communicates at the lowest level to the CPU in what's called machine code. That's the actual language that your CPU speaks. And finally, as we saw before, the CPU will delegate certain tasks to your devices over a communication channel that's known as a bus. The point is that this whole system works, but it's more optimized and faster in certain situations. Node is not particularly good at things like video processing or machine learning. these are blocking processor-heavy computations. They block your CPU, or in the case of machine learning, sometimes your graphics card, or GPU. They're possible, but Node won't really give you many advantages over other languages and runtimes. What Node is really good at is servers, and the many various things that servers do, like talking to databases and coordinating with many other servers and services on the web for things like emails and authentication. Node works really well when your main performance problem is input and output rather than heavy calculations. It works best when we can delegate these tasks to our operating system and the devices on our computer. If our code blocks in JavaScript, or we're using the CPU heavily, then our event loop will get stuck, and Node won't be able to manage the other tasks happening side by side efficiently. On the other hand, Node is really good at serving data for I/O-heavy applications, which just so happens to be most of what we do on the internet. For example, video streaming like Netflix is mainly input and output, sending video files from a database of videos through a server like Node and into a user's web browser, or a Netflix application. In fact, this is how Netflix actually works, using Node.js. Fortunately for us, the Node model aligns really well with how modern web applications are built. They take advantage of existing technologies like databases and various services on the web that we can put together to make something useful. Node is the glue that puts everything together. It was made for the modern web, which is why Node is doing so well. All right, let's keep going. I'll see you in the next one. Bye-bye. Now, there's one part of Node that we've been taking for granted a bit. And that's this idea that it's event-driven. We've discussed in detail the event loop, which is where our events get generated, asynchronously in the background. But what does this mean for us as Node developers? How do we react to all of the events from the event loop? The most universal way that you'll see in every programming language of dealing with events is what's called the observer design pattern. We'll talk about these design patterns throughout the course, but design patterns are proven approaches to solving problems that appear again and again in all kinds of different programs and applications. They allow us as developers to avoid reinventing the wheel, to avoid coming up with patterns of our own from scratch every time we encounter a new problem. Let's take a look specifically at the observer pattern, which is one of these approaches which we apply when we have something like, say, a celebrity, say this mysterious racing driver. So someone famous who a bunch of people, their fans, are interested in getting updates about. These fans are observers, and the celebrity is the subject of being observed. So our observers subscribe to events from the celebrity that they're interested in to get notified when an event relevant to the subject occurs. Maybe our mysterious racing driver wins a big event, a big race. This event comes from the subject, who then notifies all of the observers. As long as the observer is subscribed to that subject, it gets all the updates from it. Now, each observer can react to that event in whichever way it needs. In this case, they all seem to be dressed in lab coats, so maybe they're doctors, and they just breathe a sigh of relief that the race ended safely. Whatever the observer and the subject are specifically doing, we tend to use this pattern when the subject that we're observing, our celebrity, doesn't just trigger one event, but instead creates a series of events that can be listened to by multiple observers and can occur spontaneously, more than once. So our race car driver can win a race on hopefully multiple occasions. Or they might start driving a new car. Whatever the event, there's a many-to-one relationship between observers and subjects. All that means is that just one subject can have many observers. So what's this useful for? Celebrities can be modeled using this pattern, but a button might be represented this way as well, with button hover and click events, for example. A database can be represented this way, with data being created, updated, and deleted on different collections of data. So each of those would correspond to a different event. And as we'll see later in this course, even different messages being sent over a chat client can be represented using the observer pattern. It's really so useful and is in fact the basis for popular front-end frameworks like React and Angular. And we'll definitely be using it in this course. All right, let's take this concept and explore how we might use the observer pattern specifically in Node. I'll see you in the next video. Welcome back. In the previous video, we learned about the observer design pattern and how we could use it to model problems where some observers are watching a subject for events. In Node, the way we get notified of these events is, you guessed it, using callback functions. And we'll demonstrate this in just a second. But Node has another really useful built-in module that helps us work with events, such as those in the observer pattern, where a subject emits events to a series of observers. And that module is the events module, which we can find in our Node.js documentation, right below the errors module. If we scroll down, we can see that much of the Node.js API is built around asynchronous event-driven architecture, in which certain kinds of objects that we call emitters emit named events that cause listeners to be called. Now, what does this mean? Well, our listeners are callback functions that are called whenever one of these events with a certain name has been emitted, where emitting just means sending it out or triggering some event. Specifically, the way we do this is using the event emitter class, which is part of the events module. And if we scroll down to this example over here, we can see that the event emitter class can be used by doing the following: by calling the require function on the events module and setting that to the event emitter class. Don't worry, we'll talk in detail about the require function later, but it is what lets us use the code in the events module. And so we can use it to introduce this concept. Let's stop talking about it and see it in action in our code editor. I have an events.js file on my desktop where I'm going to create an event emitter just like we saw in the documentation by calling the require function and saying that we want to use the events module. The event emitter is capitalized because it's a JavaScript class, which we can create instances of for different subjects that we want to emit events from. So say we have a celebrity. We could create a new event emitter and say that the celebrity will be emitting events about their life. Now we can have different observers who subscribe to the events from the celebrity. So let's just say we'll have some code to subscribe to the celebrity for observer 1. And that observer subscribes to the celebrity by calling the celebrity.on function and passing in the name of the event. Remember that we can have multiple events being listened to. For example, a button click and a button hover event. Or on a celebrity, let's say we're interested in the race win event because our celebrity is the mysterious race car driver from before. And you can see that the second parameter here, the second argument, is the listener function. And we're now well aware that in Node, our listeners are callback functions. So we could say that when the celebrity wins, we call a function. And let's say this observer is our race car driver's biggest fan. So our observer will say console.log and print a message to the driver saying, "Congratulations, you are the best." Now, whenever the celebrity wins a race, this observer will print a congratulations message. So every time the celebrity emits an event with the name race win, the callback function that we registered as a listener will get executed. And we could use our function keyword here or just the arrow syntax. In fact, we could add multiple listeners for that same event, and they'll get executed one after the other. So we could copy this code into a second observer, say observer 2, And maybe this time, instead of a big fan, it's actually one of their competitors. And instead of congratulating them on their win, they say, "Boo, I could have done better than that." All right, we have a celebrity and we have a few callback functions that are going to be executed when the celebrity wins a race. But how do we trigger that race win? How do we emit that event? Well, our event emitter class gives us a celebrity.emit function. And we can pass in the name of the event to that function. So now, what will the result of this code be? So now, let's see what happens. If we go to our terminal, and I navigate to the desktop where the events file is, I can now run node events.js, and we see that the race win event was emitted, and I got the output for both listeners. And in fact, I could emit multiple times. So I could say emit a race lost event followed by another race win. And because there are no listeners for the race lost event, but 2 listeners for the race win event, we'll get the 2 messages executing one after the other for both wins. So let's see what happens. Our observers are reacting to the events in our celebrity's life. Using this pattern, we can use the event emitter module to create subjects like the celebrity, which emit events to their observers. Very much like in the observer pattern. To give you an example of how this is used in real life, let's look back on something that we've seen before, which is the node process. Remember the built-in process module that we used to get the arguments for our node process? If we go to the node documentation for process, and we click on this process events section, we can see that process is an instance of the event emitter. So just like we had process.argv, which was an array of arguments passed to node, the process object also has an on function, which can react to different events that are emitted at different stages of the node process lifecycle. So for example, we can take the code here for process.on responding to the exit event. And if we paste it into our program over here, we'll now expect to see the events that were emitted on the celebrity, but also the exit event when our program is done executing and ready to exit. So if we run this, and I'll clear my terminal, passing in events.js to node, you can see that we now get this log statement after the 3 events were emitted. So first the celebrity won a race, then they won another, and our program no longer had any code to execute, so the exit handler was triggered. You might have noticed that we're also passing in an argument to this event, which is the exit code. 0 for a successful normal execution with no errors, and a non-zero number for when there's an error. What Node does is it emits an event when it's ready to exit the process, and then exits immediately after this callback is executed. To demonstrate events with arguments, we could rewrite our events over here to emit just a race event with a result. So in this case, the result would be win, or alternatively, a race lost. So now we have one race won and one lost. And in our handlers, we could respond to different results differently. So say we pass in a result to both observers, and we only execute our little log statement if the result is a win. And we do this for both. And in general, we want to put these braces around all of our statements so that it's clear what code is running in the conditional. So we'll do that. And now, with our new shiny program, we should see both of our listeners executed for the race win, but not for the lost one. Let's see what happens. So I'll clear my terminal, and if I run the code again, we get just the one message for the win. And hold on a second, we're not getting the competitors log here, so I must have made a mistake. And yep, I didn't rename my event correctly. So our race event is triggered on a race completion with a result passed in as the argument. So let's try again. And this time we get both listeners getting triggered. There we go. We've seen that celebrities and processes can both be event emitters, but many, many things can be modeled this way effectively. So it's a useful tool to have in your tool belt. And because Node uses event emitters so heavily, we'll definitely be seeing them. Until then, I'll see you in the next one. Hello! It's time to start diving into Node modules. We can't build everything ourselves from scratch, right? We want to reuse code that's been done before and focus just on the features that make our application unique. If I'm building a web server for a website on ice cream, I'm not interested in the fine details of how the HTTP protocol works and how my computer represents data in bits and bytes. That's not really relevant to ice cream. The thing that's going to make my website unique isn't going to be the way it makes HTTP requests. It's the way that I present information about my favorite ice cream. So Node allows you to reuse code, like ways to make HTTP requests using Node modules, which we can also use to break down and organize our code into smaller, more manageable files. Remember when we talked about the Node built-ins? One of these was the require function. Node adds a built-in function called require that's not part of vanilla JavaScript. This function just takes a JavaScript file, executes it, and then returns the code from that file so that we can reuse it elsewhere. We can require any of the default built-in modules, for example, the HTTP module or the events module, by passing in the name of the module as a string. And like we've seen, we generally assign the result from our require function to a variable, almost always a constant, that represents the value returned from that module. We're able to require modules that are built in, like with the events module, or modules that we build ourselves. And we can use require to take advantage of third-party modules, which are modules built and shared by other developers. We're going to explore each of these possibilities. So let's get into it. Welcome back. What can we do with the built-in modules? We have all of this functionality that we see here in the Node documentation built into Node, including working with the file system, encryption, and HTTP. We're going to do an example using the HTTP module to browse the web. We'll see what we can do using just the power of built-in Node functionality. Let's try to duplicate what happens when we visit google.com in our browser. We're going to build out this HTTP example.js, and we'll start by doing the most important thing, which is requiring the HTTP module. And we'll assign it to a constant, HTTP, which we're going to use to make a request against Google servers. Now, the require function has set the HTTP constant to the set of functions and data that are returned from the HTTP module. And one of these functions is the request function, which we can call using http.request. And we can see that it takes a string, a URL, or a request options object as its first argument, and a callback as the second argument. This is a convention that we'll see throughout Node, where the callback is the last argument that we pass into an asynchronous function. First, we'll pass in the data, which will be the URL of the Google homepage, google.com, and the second argument will be a callback that accepts a response object when it's called, which means our callback function, using our arrow syntax, will look like response and then the body of our function. The response passed into our callback is the result of making the request that we just specified. And the way we get data back from our response is by calling the on function, which takes the name of an event as a string and then a listener as a callback. Does this remind you of something? Check it out. We've already bumped into a real-life example of the event emitter in action. Very, very cool, and there's way more where that came from. So the event that we're going to be responding to is called data. And the data event has a parameter for a chunk of data returned by that event. So we can try logging the data that we just got back, and we'll use a template string to say data chunk is the chunk. A chunk is just a piece of data. That's not necessarily the whole of the response. We could receive more than one of these data events if the size of the response from our server is very large. And the fact that we can get more than one of these events makes it a perfect use case for the event emitter. Our response here is, among other things, an event emitter. And one of the other events that it can emit is the end event, which is sent when there's no more data coming in from the request. It doesn't have any parameters, and we'll just say no more data to make sure that we're getting this event. And our request has completed. Now, before we try this out, we're going to need to do something with the response result of this function call. So we'll access it by first saving it to a constant that we'll call the request. And now we'll need to call request.end. We always need to do this because the end function will cause the request to be sent. Let me show you what I mean. So I'll comment out the end call and see what happens when we execute this program, calling node http example.js. And I got this error that says invalid URL on the www.google.com address. This is because I didn't include the HTTP in front of the address. Our library needs to know which protocol we're using. And as we'll see in a second, it's very sensitive to using the correct one. Okay, so now that we've added the HTTP protocol, let's see if our program works. I'm going to clear the console and run it again. And I'm waiting here, but nothing's happening. This is because I didn't trigger the request to be sent by calling the end function. So I'm going to exit out of my program, uncomment the end, and hopefully this time it works. Let's see. That looks like the HTML to the Google homepage to me. We've got Google search showing up, as well as our HTML tags. And when we finished getting the data from Google, we got our no more data event and our log over here. So that works. But what happens if we wanted to be really secure and use the HTTPS protocol to get our data from Google? Remember, HTTPS keeps the data encrypted when it's being sent between our machine and Google's servers, so that no one can snoop on our data or change it unexpectedly. So I'll save my file and try running it again. But I got this invalid protocol error this time. This is because our HTTP module doesn't match up with our use of HTTPS. When we want to be secure, we need to use the HTTPS module in combination with an HTTPS URL. Node uses this separate module when communicating securely, and it has a similar series of functions to the HTTP module with the additional functionality for secure communication. So now when we run our program, we get the response from Google, but it's been decrypted by Node. Now, you might have noticed that we are always using the request function from the HTTP module. In cases like this, when we know exactly what we're using, it's a good idea to use this modern ECMAScript syntax to destructure the object that we get back from our require call. This looks something like using the curly braces and passing in the name of what's in that object that we're using. So in this case, we're saying we're going to be using the request function, And now the request function doesn't need to be prefixed by the HTTP dot. This is very helpful in knowing exactly what functionality we're relying on from each of our modules. So I suggest doing it whenever possible. And it makes it easy to switch if, say, we wanted to replace our function with a different one. The HTTP and HTTPS modules include a convenience function that's called get, which does the same thing that request does when we're only getting data from the server and not sending any data in its direction. The benefit here is that we no longer need to call the end function. It's called directly by get. So I'll remove that, and now I can get rid of our request variable. Let's see if things still work. Very nice. What we're doing is just like loading the Google homepage in our browser, except unlike the browser, we're not rendering the HTML that we have here on our screen. Just a little difference between our application and the Chrome browser, right? Nothing too major. All right, we're off to a good start. Remember, we've built this using purely built-in Node functionality. We didn't have to install or download anything other than the Node runtime. But we're just getting started. Let's keep it going. I'll see you in the next one. Welcome back. So why do we use modules? What benefits does learning about them give us? Well, a module is just like a box. This box contains some code which is dedicated to doing one thing well. And so we label the box with a name like http.js, which corresponds to the name of our module. We combine these modules with each other to create more complex structures, which altogether make up our program that relies on all of these modules working together to achieve our goal. I've broken down why we might want to use modules into three main reasons. The first is one that we've already seen, which is that we want to reuse existing code and not reinvent things that have already been proven to work. We want to spend our time building what's important to us and what makes our application unique. Modules allow us to package existing code into these reusable chunks. The second reason is that modules help us organize our code. And the third related reason is that they expose only the functionality that will be used by other modules and hide details that only matter within that module. Let's explore these two reasons a little bit further. So say we're looking at an HTTP module, which we want to use to make requests against the server and receive some data back in a response. Well, there's many different things that the HTTP module might do. But we know for sure that it's going to deal with requests and responses. And so that's how we might break down our modules, with a request and response.js. Each of these can be self-contained, doing just what's relevant for that part of the process. So storing only the data that's required by the response, and responding to events that we'll be getting back through that response. Our HTTP module will want to make use of both of these building blocks. But we don't necessarily need to know the details of how the response reads in data from the server, or how the request packages up our data to be transmitted over the internet. These are implementation details that are relevant within the module, but not really relevant to http.js. At this layer, we only care that we are getting back some data, and that we can transmit some data. So we load those modules and make use of their capabilities, but those lower level details remain hidden, which then simplifies our top level. Our HTTP module is now only concerned with how it uses response and request objects to do higher level operations, rather than worrying about irrelevant details. All right, with that, let's move on to the next video. Welcome back. We've used an existing module, HTTP, written by the authors of Node.js. But can we write our own modules and organize our own code? Of course. Let's do it. I've created an modules example folder. And together with you, I'm going to try to figure out the structure of the HTTP module. In fact, let's do the HTTPS module. In Node, each file is treated as a separate module. So I'll start by creating a new file called https.js for the top-level module. And let's say I want to make a function which allows me to make a request against some server to send it some data. And this function will take a URL for the destination that we're making the request against, as well as some data to send that destination. And it's going to return the response. Now, say I wanted to break out the details of the request and the response into separate files. I would create a response.js as well as a request.js. And the key for our request is a function that allows us to send it to a URL and passing in some data. And remember, this is HTTPS, which is an encrypted connection. So we're going to need a function that encrypts our data. And it returns the encrypted data. So for now, let's just say that it takes this data and returns the encrypted version. So our send function is going to take the data and encrypt it. And then send it to the URL of our server. So we're just going to say sending, let's use our template string here, encrypted data to URL. And in our response, we're going to need a function which reads in the response and returns the data that we get back, which of course needs to be decrypted because it's been encrypted by the server to keep our data private. Now, obviously, this isn't a real read function, and we're not actually decrypting any data. For that, we'd probably use a library that implements TLS, which is the protocol that our browsers and servers use when sending encrypted data over the web. But what we're interested in here is the structure. And with our functions that we've created, we can create a skeleton of this request function, where we want to send the request to our URL, passing in the data, and then read in the response, returning it from that function. But now, how do we actually use the send and read functions from our request and response modules? Right now, we don't have access to these functions because functions and variables in a module are private to that module, meaning that we can't access them from other modules. That is, unless we export them first. And the way we do this is using the module keyword. Module is a global built-in that contains data related to the current module. So for example, if I do console.log inside this module, and I run node request.js, you can see that this entire module object was printed, including things like the path where the module lives in my module examples folder, the file name, whether it's been loaded or not, but also this exports object. This object is what we need to set so that it includes all of the functions and variables that we want to be available in other modules. And we can do this by doing module.exports equals an object containing a function called send, which will set to the send function. And since we want to export the function with the same name that it already has, we can use the shorthand syntax of just saying that we're exporting send. Now, inside of http.js, we can use our require function to create a request constant that we set to our required module. And what we pass into our function will still be a string, but it will be prefixed with a ./ followed by the path of the module. So in this case, we're looking to require request.js. The ./ here just means that we're looking in the current folder for a local module that we've written ourselves called request.js. The dot represents the current folder. And altogether, our string is called a relative path. If we were looking at a parent folder, so say we had a folder called public, and our HTTPS module was in that folder, we would rename our string and use 2 dots, which represent the parent folder. So in this case, request is one level up from HTTPS. And you can see here that my code editor has made that change for me without me having to do anything. But depending on what you're using, you might need to be careful to make sure that you're looking at the right folder. Okay, but we're not going to use the public folder right now. So I'm going to move my HTTPS file back to the original folder, and I'll delete this. Notice that my file path has been updated back to the dot. And we can actually remove this .js extension because the require function by default looks for JavaScript files with the .js extension. This is set on the global require object. So if I go to my Node REPL and I look at what require.extensions is, we can see that Node has set the require function to look for JavaScript files first if there's no extension in our path over here. And if it doesn't find a .js file, it'll look for a JSON file. And finally, this binary .node file, which is an advanced feature where you can write an add-on in C++ and import it as a Node module. So for all other extensions, for these extensions, we would need to include the extension in our require statement. Okay, so let's do the same thing for our other module. In response.js, I'm going to set module.exports at the bottom of the file here to the read function. Notice that for both modules, we've set up the example so that there's a function that we want to export and one that is only really relevant within that module. How the data is encrypted and decrypted is not something that the HTTPS module needs to worry about. We only care about the public interface for the modules that we're using. So now I can create a response using the response module. And when I call my functions, I will call them using the correct constant. So request.send and response.read. Let's test this out. I'm going to make a request to https google.com, passing in hello. And in my terminal, I'm going to execute the https.js module. And it looks like I got an error. I've called my request function the same as my request module. So I'm going to need to rename this to, say, make request and call that. Okay, let's try again. Looks like our response isn't coming in because we're not logging the value that we get back from our function. So what I'll do is set it to response data and log that. Okay, third try's the charm. There we go. Our modules are being loaded. The code in them is being executed, and certain functions exported to be then used by the module here that we're running from Node. Okay, let's take a quick break, and I'll see you in the next one. Welcome back. There's a few different ways that you might see modules being exported. We can set our module.exports object all in one step and say that we even had a constant, like say the timeout, where if after 500 milliseconds the request doesn't complete, it gets aborted. And we wanted to share that with our other modules. We could add that to our exports just like that. But we could also set the properties on the module.exports object directly by assigning them. So say we did module.exports.send equals our function, and module.exports.requestTimeout equals 500 milliseconds. This would work as well. And Node even gives us a shorthand syntax where we don't need to include the module keyword, and we can instead just set the exports object directly. Exports here is just pointing to module.exports. And say we only had one function that we're exporting. Our module.exports could point directly to our function. So now this function is all that we're exporting from our module. And this changes how we access our function. Now our response over here is a function. So we could set it to read directly. And when we call it, we would just call the read function. This should still work. My recommendation is, if you have a choice, to stick with the version that we started out with, which was using the module.exports object and putting it at the bottom of the file. When you do this, it's clear what the interface to your module will be and how it will be accessed. When you're reading your code, you only have to look in one spot, rather than searching for references throughout your file. Another thing that we could do, if I move my response module back to how it was, is when importing these modules to be clear about what I'm using. Notice that in https.js, I'm not using the request timeout. So I should be clear by using this destructuring syntax that I'm only using the send function. And likewise for the read function in the response. So this is now setting the read constant to the read property returned from our response module. This change lets me call these functions directly. There we go. Now this is starting to look like a clean Node program. I'll see you in the next video. Welcome back. The modules that we've seen so far have been what's called CommonJS modules, which is a standard for modules that was created back in 2009, more or less when Node.js started. CommonJS is mostly known for being used in Node, but it's also used in a few other server-side technologies, like the popular database MongoDB. When we use the require function, we're using CommonJS. The other major standard for modules competing with CommonJS is ECMAScript modules, which are part of the ECMAScript specification that is the main standard for the JavaScript language. And it's followed as much as possible by your browser. and, for example, the V8 JavaScript engine that Node uses. ECMAScript introduced its own modules in ECMAScript 6 or ES6. So you might hear these modules called ES6 modules, or ESM for short. Rather than using the require function, these modules, if we look at the Mozilla developer documentation, under the import statement, if we scroll down, we can see that rather than using require, we call import from and then the name of our module. If you've done a lot of JavaScript front-end work, you've probably seen this import statement. Likewise, for exports, scrolling down here, rather than using the module.exports object, we use the export keyword. We'll learn more and see this in action because, finally, starting from version 13.2, Node.js began supporting ECMAScript modules, in addition to CommonJS. This is great for maintaining one context when building projects where you have a backend and frontend, and you're switching back and forth. With changes like this, it brings you one step closer to just having one language in mind, and potentially even sharing code between front-end and back-end modules. In Node, you'll mostly see CommonJS, but as time goes by, adoption of ES6 modules will get more common, and so you might see them more. But the vast majority of Node code has been written with require and CommonJS, and that will continue. So what you want to be focusing on, and what we're going to be using in this course, is CommonJS. But in case you're interested in making your own or using existing ES6 modules, we can learn a lot by comparing with CommonJS. Let's give this a go in the next video. I'll see you then. Welcome back. How would we write our modules example if we wanted to use ECMAScript modules? We need to replace our require function calls with import statements and our module.exports object with an export statement. The way this looks is actually quite similar. Rather than assigning a constant, we call import, and rather than calling require and doing this assignment, we remove that and write from. We also don't need these parentheses, but we do keep the path of our module. And that's what an import statement looks like. Something to be aware of: when using CommonJS modules and the require statement, you might hear import used as a synonym for require. That is, you might hear, "Hey there, I'm importing the Express module," or "Hey there, I'm requiring the Express module." You might hear either version. So it's good to make sure you're clear about which type of module you're working with, if there's any doubt. All right, we'll do the same thing for both. And now we can use the send and read functions that are being exported from our modules, this time as ECMAScript 6 modules. Now in our response.js, we'll replace our module.exports with a call to export, leaving everything else exactly the same. And we'll do the same in both files. Now we can try to see what happens if we run our module through Node. We get an error that says that we cannot use an import statement outside a module when we try to import our send function from the request module. And scrolling up further, we see this warning that tells us that to load an ES module, we need to set type module in the package.json, which is something that we're going to be exploring, or that we need to use the .mjs extension. You see, Node treats JavaScript files as CommonJS modules by default for backwards compatibility. Node has been using CommonJS since it was created. You need to explicitly tell it to treat your code as an ECMAScript module by naming the file with the MJS extension, where the M is for module. So let's make that change. We need to rename each of our modules from .js to .mjs. There's one more change we need to make. If we go to the Node documentation, under ECMAScript modules, and we go to the terminology section, we can see that for relative paths, like when we're using the // or // for the parent or current directories, the file extension is always necessary when importing the file. Unlike with require, where the file extension is assumed to be .js in the majority of cases, with import, it's a good idea to use the extension, which is going to be .mjs. Let's make the change in our http.mjs file. This is what our import needs to look like. You might see some code bases that don't require that extension. For example, if you're using some kind of compiler that handles that extension for you. But in general, it's a good idea to use the file extension for better compatibility. If we're already making the change to ECMAScript modules, which brings our code closer to how things work in the browser, we should follow the same conventions for using the full name of the file, including the extension. This way, your modules are more likely to be compatible with browsers, but also with other JavaScript runtimes, such as Dino, which always uses the full path or URL to the file that you're importing. With these changes, we can now run our code, and we have to be careful to run https.mjs this time. There you have it. Node using ECMAScript modules. That wasn't too bad, right? All right, I'll see you in the next one. Welcome back. When we load a module, whether it's in CommonJS using the require function or an ECMAScript module using the import syntax, Node caches that module. Let's explore what that means. Say our request.js file, in addition to having all of these assignments and functions, had some code that executes whenever it's loaded. So say we had a console.log here that just said, hello from request.js. Now, what happens when we run our program? Well, the first message we get is hello from request.js, which makes sense. We're calling require on request before we call any of our functions, before we start making our request. But what happens if I call the require function more than once on that same module? Say I made a mistake here, or I just split up my statement and I imported the request timeout separately, rather than putting it all on one line. If I run this program, what do you expect the output to be? Pause the video and take a moment to think about it. You may be expecting that our message in request.js is printed twice, once for each time the module was loaded. But if we actually execute our code, and I'm going to clear my terminal here, you see that we still get our message, but it's only ever executed once. Why is this? Well, in larger programs, it's very likely that we might have modules that are required in multiple different places. So if we had a module for just HTTP without the encryption and the security that HTTPS gives us, we might still require our request module and use it throughout that file. It's likely that some of our modules will be loaded in, required in multiple different spots. And so, in order to be efficient and to prevent behavior that's part of that module from being run over and over again, Node maintains a cache of required modules, which is basically a little database of these modules that Node checks to see if a module like request was previously loaded. And if it already was loaded, it doesn't load it again. It just looks up the module in that cache. This way, the code in our module only ever has to be run once. After that, it's already in memory. And the require function will always look the module up in the cache if it's already there. This cache is global, and it lives under this require.cache object, which we can print to see what it contains. After requiring our modules, we can scroll up and see that the cache has all of our modules, including their path, any exports they have, and also whether they've been loaded or not. So in this case, the HTTPS module hasn't been loaded by the require function because, well, HTTPS is the module that we're running. It's the one that's loading all of our other modules, which we can see below. For our request module, we now expect to see the object that is being exported, which is then returned from our require function, and also that scrolling past this parent, that it's been loaded. And this parent is just a reference to the module that is doing the loading of our request module. And we expect to see the same thing for our response. There's our response module with just the one function being exported. And we can see that it has been loaded. This require.cache object isn't something we'll be working with very often, at least not directly. But we can see that the internals of Node aren't magic. Node is using this require built-in module and its cache object to implement our CommonJS module functionality. Oh, and by the way, you can't edit a required module. Say in my http.js file, I try to reassign request.send to my own function that just logs custom send function. This is something that first-time Node developers often try to do. And all it does is that it sets the send function within this module to be the custom function. So if I did request.send here, and I try to run node http.js, I do get the custom send function, but if I called request.send in https.js, it's still calling the original function that is in our require cache, the function that was originally exported from our module. We now have a solid understanding of the Node module system. Let's keep this in mind as we build our Node applications. With that, I'll see you in the next video. Welcome back. When working with Node projects, you might come across a file called index.js. Let's explore exactly what this file means and how it might affect us. Say we wanted to organize our example a little bit more, and we wanted to create a folder, say internals, inside of our module's example. And this folder was for the request and response modules, which have to do with the internal representation of how the HTTPS module works. What would happen if we tried to require that internals folder? Say by doing require and then passing in the path of that folder. As it stands, this wouldn't work. Internals isn't a module that require can load, but we can make this work. And the way to do this is to use index.js and creating a file with that name inside of the internals folder. Index.js is a special case in Node. It allows you to treat a folder like a module, so that when you pass the path to a folder to the require function, it resolves to the index.js file inside of that folder. Let's see this in action. The index file will export, just like we've been doing, an object that contains the data we want to export from this folder. So we're going to have request which is going to point to the loaded request module, which we can do by saying request is equal to require and passing in the path of our module. Now, when the path to the request module is passed into require, the return value is this object that we set to be exported. And that object can now be accessed using the request property that's being exported from index.js. So now when we import this in http.js, we can call for our request module internals.request to access the request timeout and send function. This would look like internals.request.send. And we could do the same thing for our response, calling it in the exact same way. internals.response.read. Now, if I execute the module, everything works. Index.js is a special case that allows you to export functions from many different modules that live in a single folder from a single point, which can then be referenced using the name of that folder or the path to that folder. This way, when you import your files, you don't need to target the individual modules in your directory, looking up the specific paths. The developer just specifies one time what is being exported, and then every time it's imported, you just point to the folder containing those modules. Now, we could be really fancy here and say we wanted to export the functions directly from index.js. Say we had request and response, and we wanted to export request.send as send and request timeout from the request module, as well as read from the response module. And we wanted to do this so that in our HTTP module, we could call internals.send and internals.read directly. Or using our destructuring syntax, we could destructure those two functions from our internals folder. This way, as the person importing from the module, you don't need to worry about the internal structure of where the send and read functions come from. So you'll often see this kind of pattern with index.js. And sometimes, if you're being really, really fancy, you could do this same code by using the spread operator. So we could, instead of setting everything manually, we could do module.exports equals the request module, as well as the response module, which we spread using these three dots. And we don't need these separate imports now. This spread operator takes all of the properties in our two modules, and it unpacks them so that the same properties with the same names exist on our new object here, without us having to do it for every single property like we did before. So we could test this out, and there we go. Now, don't worry if this seems a little bit too much for just a simple export. You might prefer doing the long-form version of this, being more explicit like we did on top here. And you might prefer not using index.js at all. But the important thing that we've learned is that we can use this feature of Node to import groups of modules that are grouped in a folder with an index.js file telling us what is being exported from that folder. All right, on to the next video. Welcome back. Should you use index.js in your projects, or should you not? That is the question. This is a controversial subject among Node developers. Some love it for its ability to simplify imports and make it easier to use complicated modules with dozens of files. And some developers will suggest that you always use the direct path to your module, not relying on any special behavior in Node. Through all my experiences working with Node, I've generally learned to prefer not to use index.js for most projects. It's good to understand in case you see it, but it might add some unexpected confusion. If we look at the Node documentation for how the require function finds the module that you specified, it's actually quite complicated. We've already seen that there's different behavior for built-in modules, where you just pass in the name of that module, versus modules that we've written ourselves, which begin with the // or .. And index.js adds on to this logic. We can see that there's a section here for loading the index. It adds another special case to this already fairly long logic. It might not seem like such a big deal, but it's actually one of Ryan Dahl, the creator of Node, one of his 10 regrets about Node.js, which he presented at this large JavaScript conference in 2018. In his own words, it needlessly complicated the module loading system that we've been talking about in this section. Now, to be clear, Ryan in this talk wasn't saying that Node.js was a mistake. It's more a reflection of what he might have done differently, looking back on the past 10 years at the time in hindsight. One of those things was index.js and the complex logic that we saw just a second ago around how require loads modules. The good news is that we don't have to use index.js. We can keep things really simple. If you can avoid a few of these little missteps, which I'll make sure to point out to you, Node becomes this really, really amazing tool. Now, it's not the end of the world if you use index.js in your projects. I've used it on a few, and things turned out just great. but it's one of those things that over time you learn to be careful with because of the potential for this added confusion among developers. I hope this can be helpful if you ever come across a debate about whether using index.js is more helpful or more harmful. You can now reference reliable sources like Ryan Dahl's talk and the Node.js documentation over here, which I'll link to from this video, to talk about index.js and potentially the complexity that it might add. With this additional knowledge, we can take one step closer to being senior Node developers with an understanding for some of these little quirks in Node.js. All right, I'll see you in the next one. Hello! Sometimes, when we're building something that's really going to be great, the built-in tools aren't enough. And we want to do something more than what's available out of the box. Or we just want things to be more convenient. We want it to be easier to make requests, create servers, and talk with databases. For this, modules released by other developers, or what we call third parties, are useful. After all, it's only when collaborating with others that we can get our best work done. The good news is that Node has this really, really large ecosystem of libraries, or as we call them in Node, packages. Packages are these bundles of code that we can reuse. And we can find them on this site, npmjs.com, named after the Node package manager that we use to install and create these packages. When we talk about NPM, there's two things that we might be talking about. The first is the npm.js website and the collection of code available through it. The second is a tool that you downloaded when you installed Node. In our command line, just like we have Node that we can use to run the REPL and execute our Node code, we also have access to NPM, which is also a command line tool. We use this tool to manage and work with all of our NPM packages. Because NPM is bundled with the Node executable, it creates this centralized collection of code. If there's some code we want to reuse, we don't have to search all over the place on different websites and repositories to find it. Instead, we can look in one place for the collection of over 1 million packages that's available at npmjs.com. It's one of the largest collections of code in the world, and it's all completely free to use. This is one of the things that makes Node so unique and successful, because so many developers use Node and create packages, sharing them freely on this site. Even more developers join in, creating this healthy cycle where more developers want to use Node and contribute to it. This philosophy of sharing and open source has been central to Node's success. We get more learning materials, but also more existing building blocks that we can use to build up our awesome Node applications. Say we were interested in working with a database, something like PostgreSQL. We could just look for the tool we're interested in this search bar, so Postgres, and we get this list of all the packages that are related to our topic, giving us a huge head start in building our application. Let's learn all about what packages are and how to use NPM to add them to our projects and work with them in the coming videos. I'll see you then. Welcome back. Let's get right into it. How do we create NPM packages? But before we do that, it's worth clarifying one thing. What's the difference between a module and a package? We've learned that a module is a file that contains some code which may be exported from that module. On the other hand, a package is kind of like a collection of modules that have been packaged together. Let's make our first package and see exactly how it does this packaging. Looking back at our example from the previous section, we had a couple of different modules. Now, what if we actually wanted to implement this makeRequest function using a package that's been shared on NPM to make our life easier when filling out some of this functionality, like actually sending a request rather than just logging that we're pretending to do so? We might go to the NPM site, and because we're searching for help making HTTP requests, we could do a search for HTTP. And we get some really good options here that are quite popular and well supported. We have Node Fetch, which gives us an API similar to that which we get in the browser on the window.fetch function. We have Got, which aims to give us a more user-friendly API with a few more features. And we have Axios, which is a powerful middle ground between those two other options. So say we chose Axios. We now know that the name of our package is Axios, and we have this install command here, which I can click to copy that command, which gives us our first NPM command, the install command. And so if we wanted to install Axios, we could try pasting that command into our terminal. And the I here just stands for install. So we could either type npm I for short or write it all out with install. But when I run this command and I scroll up here on the input, you can see that I got an error. No such file or directory as package.json. This is because to install packages, we first need to initialize our Node application with the npm tool, which will create this file for us. We do this by typing the npm init command. I'll clear the terminal here so we can see what's going on. And when I run this command inside of the Node modules example folder, I get asked a series of questions. The command first asks me what I want the package name to be. And if I just press enter, it will default to the name of the folder. And I'll get asked a few more questions. What version number? What the description should be. And I can just press enter through all of these options to get the defaults. The command will verify with me what the resulting package.json file will look like, and we'll get into this in just a second. So for now, we're just going to say, okay, yes. Now, if I knew I was going to take all of the default options for the package name, the version, description, and so on, instead of going through all those options, I could just type npm init-y, where the -y flag just means that I'm saying yes to all the questions, or giving the defaults for all the options. Either way, we can now see that we have this package.json file inside of our project, inside of our example folder. Our little program here has now been initialized as a NPM package. And this package.json file describes that package. We have a name, a version number, a description. We have main, which describes the entry point for our program, what file to execute with Node by default. And then we have this script object, which allows NPM to be used to automate common tasks with our package, such as running tests or running it in different configurations. For example, as a development version versus as a production version. We can include ourselves as an author, and we can also specify the license, telling other developers how they're allowed to use our code. So I'll save this for now. And because we have a package.json now, we can npm install our Axios library. Let's see what happens. Scrolling up, we no longer have an error. And we can see that Axios was added. If we close our terminal, we can now see that package.json has added this dependencies field now automatically, which keeps track of all of the packages that we've installed, as well as the version that we're using. We could now add a script, adding a property here called start, and setting it to the command that we want to run to start our application. In this case, we want to run node https.js. So we've got the name of our command and then the command that will be run. Now in my terminal, rather than typing node https.js, we can write npm run start. And that will run our start script. Or specifically for the start script, we have the shorthand of typing npm start. For most scripts though, we'll need to type out the full npm run and then the name of our script. We've now successfully installed our first npm package. Congratulations! And you may have noticed a few extra files and folders that were created in the process automatically. I wonder what those do. Let's keep digging, but first, let's take a well-deserved break. I'll see you in the next one. Welcome back. Why did we need to initialize our package to install our Axios dependency? Well, we needed our package.json, which only exists for Node packages. You see, most Node programs are actually packages, and they need to be packages in order to really make use of NPM. You may not choose to share it with the public on a site like npm.js, which is a database of all of these available packages that we call a registry, because all of our modules have been registered on it. So you might not publish your package here. But as long as you have this package.json and your application is managed by NPM, meaning that you can install dependencies and run scripts, that means your application is a package. However, when most people talk about packages, they're talking about reusable packages, like the ones you install with NPM, like Axios. So for the purposes of the rest of this course, package means a reusable package that's been shared on our NPM registry. Okay, let's get into some fun coding. I'll see you in the next one. Welcome back. It's time to put things in action and see some third-party code being put to use. Let's start with a fresh package example folder. And the first thing we're going to do is npm init to create our package.json. And we'll pass in the Y flag just to get our defaults. And now we're going to install the Axios library, which we're going to use to make a simple request against Google's servers. So we have to make sure to npm install, which does two main things. First, it downloads all of the code from the Axios package into a folder called Node Modules, which we can see here. And second, it automatically modifies our package.json to keep track of the Axios library as a project dependency. And it also tracks the Axios library inside of our package-lock.json. We'll talk about those in a moment. But let's start by putting our Axios library to use. And we're going to do so inside of a file we call request.js. The first thing we do is always to require our Axios library. From there, let's find out what functionality Axios allows us to do. We can always start on the Axios page in our NPM registry. Scrolling down, we'll see some documentation. So let's look at the features. Axios works both in the browser and Node.js. it does this by making use of the appropriate APIs on both. So in Node, it'll use the HTTP module that we've already seen and used. And on the browser, it'll use similar functionality using this standard XML HTTP request, which is available in all browsers. But in addition to doing what we can already do, it also supports a promise-based API that we can use with modern Node features like async await. This will make it a lot easier to use and to do things like handling errors. It also adds some additional functionality, like automatically transforming and handling JSON data. This will be really useful because many of the APIs that we use on the web, that we get from these services, which we can use to send emails, for example, or authenticate with Google, almost all of those services use JSON. So we want it to be easy and automatic to work with that data. And there's some more functionality, like we can cancel requests once they've already started. And we can do things like checking on the progress of a request to see how far away from completion it is. Say we were doing a large upload, and we wanted to know how long it would take. Now, what does this promise-based API look like? Let's do what we did with the HTTP built-in and see how it looks with Axios. Remember that we made an HTTP request to get some data from Google. We can do this using the Axios.get function and pass in the address, whether it's HTTP or HTTPS, as a parameter. But rather than using a callback and passing it in as the second parameter, we're going to use this cleaner promise-based syntax. We're going to say once Axios.get has gotten the response from Google, so .then we're going to do whatever we pass in to this callback function. And this callback function takes in the response with which we can do something like, say, print out the result. Now, again, I'm using the arrow syntax here, but we can use this fancy VS Code feature here to convert it to an anonymous function. We could type it out this way as well. And by hovering over it, I can convert it back. Both ways work. Let's test this out. In my terminal, I'll do node request.js. Check it out. We already have the functionality that we got from the built-in HTTP module. But we can actually do so much more. Say I was a bit tense, and instead of typing www, I typed a few extra W's. This is now an invalid address. So if I make this request and I rerun the program, I get this long error here that tells me something about an unhandled promise rejection warning, because my address on the internet wasn't found. The good news is that I can handle these errors really easily using the .catch function that promises give us. So I'll chain the .get function with .then And then we're saying if either of these two blocks here failed, then we can catch an error and we'll get back this error object here, which gets passed to our callback function in this block. And I can log this error. Now, if I rerun this application, I get this nice looking error object that's being printed out, which is much easier to read and gives us some extra information on why that request failed. This is already extra compared to what the built-in module gave us. Now, I could also keep chaining more functions. If I wanted something to execute whether there was an error or not, I could add another .then here, which gets executed when all of our handling above has completed. So this happens when we're all done, regardless of what happened above. So we got our error, but at the bottom, we get our all done message. Now, because Axios is returning a promise, we can choose to use the .then syntax or the .then functions that are returned from this promise object that is returned from axios.get. And the reason why we can keep chaining these functions is because each of these .thens or .catches returns their own promise, which when it completes, or as we say with promises, is resolved, allows the next callback in the chain to be executed. Now, remember, our example here is now a Node package. So if we wanted to npm start it, we would add start as a script in our package.json. And we would point it to run node request.js. So now in our terminal, and let's fix our request so that it's pointing to the actual Google address. And now in our terminal, we can do npm start, getting back the success response from Google. We've now unlocked the power of third-party modules with their easy-to-use promise-based APIs, which means that we're nearly ready to start making projects. But first, I don't want to leave you hanging. Let's find out about that Node modules folder and the package-lock file. These are two things that we'll be seeing a lot, so I want to make sure that their purpose and behavior is really super clear to you. I'll see you in the next one. Welcome back. So what's the deal with this Node modules folder? Well, it contains all of the modules that we install from NPM. It's in the root of our package, right next to our package.json file. When you run npm install on a package like Axios, that package is downloaded from the NPM registry, and it's saved in your Node modules folder. Node now knows to look up that dependency in your Node modules folder when you call the require function. If we open up the Node modules folder, though, we see that there's two folders here. One for Axios, but then one for follow redirects, when we've only installed one package and included it as a dependency for our application? What's going on here? We must be missing part of the picture. Well, each of these folders contains the full source code for that package. We can actually learn a lot just by browsing it and seeing how things are implemented. And we could even update the code to any of these functions, and that's the code that would be used in our project. But this is a bad idea. The code and files that are in our Node modules folder should always be managed exclusively by NPM and through your package.json. If somebody NPM installs all of the same packages and package versions that you've installed, they should be able to replicate the Node modules folder that you have in your project. Okay, so we're not modifying the code here. But where is this second folder coming from? Well, if we go into the package.json for Axios, which we can actually browse, and if we scroll down to where it says dependencies, we can see that Axios depends on one library, and that's the follow redirects library, which is a version of the HTTP and HTTPS modules that follows redirects. So it follows the link if a web server has been configured to redirect you. Say if you're using a URL shortening service. In these cases, the follow redirects package will handle the request properly. So because Axios requires this package, NPM includes it in our Node modules folder. You see, the Node modules folder doesn't just have your direct dependencies like Axios, but also the dependencies of those dependencies. Our dependencies create what's called a dependency tree. Much like our modules, which also created a tree, we have our package that we've installed, which depends on this follow redirects package. And so we need to include both in order for our application to run. If Axios depended on another library, another package, we would need to have that package installed in our package as well. Rather than JavaScript files, which in Node are modules, we have these groups of modules, which we call packages. But the relationships still apply. When NPM looks at these dependencies, it throws them all under the Node modules folder, all side by side in this flat structure. Rather than having follow redirects inside of Axios, we put it beside Axios so that if another package wants to use follow redirects as well, we don't have to duplicate it in our Node modules folder and have many unnecessary copies of it sticking around. There's this running joke in Node that the Node modules folder is the heaviest object in the universe. If you search Node modules under the Google image search, this is probably one of the first results you'll find. And this is all because Node modules gained a reputation for growing in size really quickly for large Node applications. And it can get quite large. But the truth is that a lot of the bad reputation that Node modules gets comes from the early days of Node, when our dependencies were duplicated and when we would have to do things like remove the Node modules folder if things became corrupt during an install, which would happen fairly often. Nowadays, though, as Node developers, we don't have to worry about this. NPM has improved exponentially, especially in the past few years. Now, when we share the source code to our application, we generally don't share the Node modules folder. Just like I mentioned a minute ago, it should be generated from scratch by running the npm install command. So if I delete this folder, move it to the trash, and run npm install, I should get the exact dependencies that my project needs. This npm install command is something we're going to be running a lot when downloading existing Node projects. So we're going to get very comfortable typing that command. And I may have to refresh this folder, but the Node modules are now in the exact same spot from when I deleted it. Because of this feature, if you're using a repository for source control, say Git, you'll see Node modules added to a git ignore file, so that Git doesn't include it as something to be tracked and saved in your repository. We can see an example of this in the Axios package. From the page on NPM, we can browse to GitHub, where Axios is hosted, right here under Homepage. And in our repository, if we scroll down, we see this .gitignore file. And under this file, we have the list of things that we never want to include in the repository, including Node modules. This would just be a waste of space. All right, so we've learned how NPM manages the Node modules folder and how this folder contains all of our dependencies and any dependencies in the overall dependency tree that we need for our Node program. And it includes them in this flat folder structure so that our Node modules folder doesn't become that giant black hole from the running joke. But what about this package-lock.json file? Let's find out in the next video. Welcome back. Before we get into the next video, I want to take a moment to mention semantic versioning. This is a way of versioning packages that uses these three numbers separated by decimal points. We have the major version, which comes first, followed by a dot, and then the minor version. The major version is for when you make completely breaking changes to how the package works. It's almost like releasing a completely new package. The minor version is for decently sized updates that add functionality, but do so without breaking compatibility. So maybe you're not changing any of the existing functions and how they work, but instead, you're just adding more options. That would be a minor version update, where you would increase the minor version, but not the major version. And finally, we have the patch version, which comes last and is generally just for smaller bug fixes. Why am I mentioning this? Packages in your package.json use semantic versioning to version dependencies. Although, be careful here. Like every convention, it's up to the package authors to actually follow that convention. If we were releasing our package, it would be up to us to ensure that for a minor version increase, that there were no breaking changes. This is one reason why it's better to go for widely downloaded, well-supported packages over relatively unknown ones. It's more likely that all those users are going to keep the package authors honest when it comes to following semantic versioning. With that out of the way, let's get into the next video. Welcome back. What is Package-lock.json? Last but not least, this file makes it easier to work with a team of developers, and it helps us avoid bugs. How? Well, the Package-lock.json is automatically generated when we run any NPM commands where the node modules folder is modified, or where the package.json is modified. It's kind of like a much more specific description of the dependencies from our package.json. It includes not just the dependency and the version number, but also exactly where that dependency is coming from. In this case, our NPM Registry. It verifies that the package is not corrupt with this integrity check. And it also includes the versions and information for all of the dependencies in the tree, not just our direct dependencies. You may have noticed that the package.json has our semantic versioned dependency, but it also has this caret symbol here, which is a feature of NPM that tells it it's allowed to install any version of this package as long as it's not a major version update. And there's a special case where if the version number is less than 1, the minor version counts as the major version. Because for pre-1.0 packages, they're more likely to be changing very often. Because this versioning can be fairly confusing, the people at NPM created this handy NPM semantic versioning calculator, which I'll link to in this video. We can type the name of a package that we want to check here, and then we can test out which of the versions a specific range will capture. So if we type 1.0.0, we can see that just that version will be matched. If we type 1.2.0, but we add the caret symbol at the front, we can see that all of the versions that are above this minor version, but still part of the same major version, are matched. So we have 1.2 versions and 1.3 versions also being matched. But remember the special case. So if we had version 0.8.0 being matched, this caret symbol here is now only matching the patch versions that are greater than 0.8, but not 0.9 versions. So it's kind of like treating the 8 here as a major version, and then saying that only the next place over is allowed to increase. If you're finding these rules confusing, head on over to this calculator and play around for a bit. Everything should make sense very soon. I'll just mention one more special syntax that we'll see in our packages. Say we were matching version 4.16 with all of these patch versions available for it as well. We could type 4.16.0 and it would match all of the 16 and 17 versions. But if we only wanted to match the patch versions, we could use this tilde character instead of the caret. And this matches only version 4.16 patch versions that are greater than 16.0. And if we change this to 4.16.4, it matches only the versions greater than that on the same minor version. Okay, back to our code. So this line here is only loosely describing the version of Axios that will finally be installed. So in our package-lock file, we have the exact version that we're using for all of our dependencies. This means that if someone else is trying to set up their project the same as we have ours set up, with the package lock, they'll be able to get exactly the same dependencies, making sure that the minor and even the patch versions match up. It's even helpful if you just want to test something out with a different copy of your project and you want to make sure that you're NPM installing the same versions of your dependencies. Remember, following semantic versioning is ultimately up to the developer. And so if one of our packages has a breaking change, maybe the developer didn't realize that it was breaking, and we've now received the update for that package, this could lead to a new bug. This is why when we share our source code, it's a good idea to include the package-lock.json file to avoid any issues with semantic versioning. Let me show you an example. Say I removed the package-lock file. And I also removed the Node modules folder. Maybe when I was writing this application, we had an earlier version of Axios, say version 0.21.0. And I was still using this caret, which means that for pre-1.0 versions, patch version updates are still accepted. And for later than 1.0, minor version updates would be accepted as well. So Axios is 0.21.1, But when we were developing this, we were at 0.21.0. So now my coworker comes and tries to set up this project. They'll go in and npm install, which will go ahead and download the packages and create our node modules and the package-lock.json. But if we look in the package-lock.json file, we can see that the version installed was actually the latest version with the .1 patch update. So my coworker is now running different code than I was, which at the very least can lead to a lot of confusion if there's a difference in behavior. If I had shared my package-lock.json file with my coworker, we could have avoided this exact situation. We'd have that extra guarantee that what I experience on my machine is exactly what they will experience on their machine. And that's what package-lock.json does. I'll see you in the next one. Welcome back. Let's talk about hackers. It's common for security issues to be found in some of your packages. Any complex piece of software will have some issues over its lifespan. And there's so many Node packages around for us to use on NPM that it's likely you'll run into one of these issues soon. And it's very possible that this will be a serious security issue. That's okay. It happens. The best way of dealing with keeping your application secure is reacting quickly to keep it updated. Security is a cat and mouse game of hackers finding issues, exploits, and security vulnerabilities, and developers doing their best to patch those issues and make our software more resilient, making it safer against future security issues. Let's look at an example. When we were writing this code, let's pretend that the latest version of Axios was 0.20. And so that's the version we specified in package.json. Let's remove our existing node modules and let's see what happens when we do npm install. Node successfully installed the 0.20 version of Axios, but it's also telling us that there was a critical security vulnerability fixed in version 21.1. We can look up more information, but we also get this notification at the bottom, telling us very clearly that one high-severity vulnerability was found. To do our part in keeping our Node applications secure, the team at NPM has included this useful tool to audit our packages, meaning we can write npm audit to see if there are any security issues in any of the packages that we depend on. So if I run this, I get this notification here that there is a high priority issue that allows for server-side request forgery. That doesn't sound too pleasant. Because Axios makes requests against the internet, we need to make sure that it's talking to all of those servers available around the world in a secure way. If we don't, we're exposing ourselves pretty dangerously. So NPM audit has told us that there's an issue. And now we can run npm audit fix to resolve this issue. Basically, just by updating our package to now use, check it out, the latest version. So when writing Node applications, we want to take those warnings that we get from npm audit very seriously. And we want to make sure to run npm audit on a regular basis. Now, this isn't a magical silver bullet. npm audit will only report issues that have been reported, that have already been discovered. And it can only fix them automatically if there's an available update. If there isn't an available update, it might be worth switching to an alternative library that is more secure. All right, I'll see you in the next video. Welcome back. Let's look at how we might use some useful tools taking advantage of NPM to make our life as developers more convenient. So far, we've been installing our packages locally, which just means that they're saved to our local Node modules folder, specific to our Node project. The benefit of installing these packages locally is that we can share projects with our package.json and package-lock.json and then have our dependencies be installed with npm install. There's this really useful tool called Nodemon available on the NPM Registry. This helps us write Node applications by automatically restarting our application when any of our source code files are changed. We do this just by replacing our node command with the Nodemon command. Let's install Nodemon and see this in action. So in our terminal, we'll do npm install, passing in Nodemon as the name of our package. Awesome. Nodemon has been installed, and we see it under our dependencies, just like we expect. Now, the difference between Axios and Nodemon is that Nodemon is an executable. We use it to run our Node code and restart Node if there's been a change to our source code. So one way that we can run Nodemon is by adding a script, which uses it. Say we added a script called dev, short for development, and we did exactly what we do above, just saying Nodemon request.js. We can now run npm run, passing in the name of our script, so dev, and Nodemon will execute our request. But now if we change our source code, say instead of google.com, we want to make a request to wikipedia.org, when I save the file, you can see that my code was executed automatically. And without having to type npm start or node request.js, I have the new output from my program. And I have the source code to the Wikipedia homepage instead of the Google homepage. This makes development a lot easier. Say I had a syntax error and I put 2 dots here, and I saved my program, I immediately get feedback saying that the app crashed, that there was a syntax error, and we had an unexpected token of this dot. So we'll be using Nodemon a lot in our development. But say we wanted to run Nodemon without adding it as a script. Maybe we want to run it in our terminal. Just like we run Node, we want to be able to run Nodemon, passing in any source code file that we want. Well, the terminal will give us some message telling us that Nodemon is not a command that's recognized. Unlike Node, which was installed to be recognizable in our terminal, to be in the path that we use, Nodemon is installed only in our Node modules folder. Now that I've refreshed, I can see that Nodemon has a lot of dependencies that we now need to install. But if I go to this bin folder here, actually not in the Nodemon folder, but instead there's a .bin folder here right at the top of our Node modules. This is where the actual Nodemon executable is available. So if I wanted to run Nodemon as a command, I would need to pass in the path starting with // for the current directory in the Node modules folder and the .bin folder inside Node modules, and only then passing in the Nodemon name. So this should work. There we go. But we pretty much never run things this way. It's not very convenient. What if we wanted to use Nodemon in all of our Node applications, anywhere on our computer, and on any project without specifically installing it for that project? For this, NPM gives us the ability to install modules globally. We do this by typing npm install and passing in this -g flag, G for global, and then passing in the name of the module, which we want to be available anywhere. So when I run this command, we can see that Node is installing Nodemon again, and this time, instead of installing it to our Node modules folder inside of our package example, it's been installed to the Node modules folder in this directory, in this folder on my machine. That's specific to my installation of Node, rather than being specific to this package, to this application. And because this time it's been installed globally, now we can, anywhere in our terminal, type nodemon and the name of a JavaScript file, and Nodemon will execute. So now we don't have to have all of these dependencies installed in our local project. In fact, we can even npm uninstall Nodemon, and we're not passing in the -g flag, so this will uninstall Nodemon from our project here. If we refresh our folders, you can see it's disappeared from our Node modules folder, but we can still run Nodemon in our terminal. Check it out. If we're using this tool in multiple projects, this will save some space on our machine and be a little bit more convenient. But it has the disadvantage now of making my package.json less representative of the things I need for my program to work the way I expect. Now there's some external dependencies that need to be in place before I can run this program, at least in development mode. In general, I would suggest against installing things globally, because we want our source code and all the files in our project to be as self-contained as possible. That's what package.json and NPM are really all about. So with that, I'll see you in the next video.
Hey peeps, amazing work making it to this point. You've made it to the best part. In this final section, you put your skills to the test by building a wicked planets finder project. I won't talk about it too much and let you dive right into it with Adam, but I quickly wanted to let you know that you can find the final code for this project in the description down below. Keep in mind, we really recommend that you code along with us and only use it if you're really stuck or are having some sort of problem. That's all for now. Have fun building.
Hello! Now we're getting to the good part. Why? Because we're going to be putting together all this theory that we've learned into an example that I'm personally super excited about. We're going to be exploring space, planets beyond our solar system, and finding those planets that are most likely to be habitable. That means planets that humans could one day live on, or potentially planets that might already support alien life. And we're going to be doing all this in Node, using what we've learned so far. The story starts with the Kepler Space Telescope. This was a state-of-the-art telescope launched into space in 2009. For nearly 10 years, it looked out into space and gathered data about planets beyond our solar system. Kepler observed hundreds of thousands of stars, and in doing so, helped us discover over 4,000 planets. And the best part? NASA shared all the data that Kepler gathered, which means that we're going to take a look. We'll get started in the next video. See you there. Welcome back. All right. How are we going to do all this exploration of space using the data that Kepler found? Well, we're going to be getting our data from the NASA Exoplanet Archive. Why exoplanet? Well, exoplanets are just planets that live outside our solar system. They orbit other stars other than our sun. And we're going to download the table of data gathered specifically by the Kepler Space Telescope. which we can find under this link for KOI table, where KOI is the list of Kepler objects of interest, the list of things that Kepler observed that might be stars containing planets that could potentially be habitable for humans. Let's check it out. We have our Kepler data, and we could explore it here, but instead, we're going to download this table of data in what's called a CSV format, and we're going to read it with Node. So let's save that to our machine. Once our file is downloaded, let's move on to the next step. In VS Code, I've opened a planets project folder, and I'm going to copy that file we just downloaded into the folder. And let's just rename this file to, say, Kepler_data.csv. Okay, so what is a CSV file? CSV stands for comma separated values. Let's see what this looks like. The file starts with this comment here saying that this file was produced by the NASA Exoplanet Archive. And we can see that because it's a comment, it starts with this hashtag symbol. This is followed by a list of all the columns in this data file, which are also comments, and they have pieces of data like the name of the planet, things like the orbital period of the planet in days, and even things like the radius of the planet. And then there's some interesting information here around the star which the planet orbits. So the effective temperature in Kelvin of that star. Or even the amount of gravity on the surface of that star, or its radius. This is all data that we can explore. All right, now below all of these columns, the next line in our file is this header of our CSV file, which contains a list of all of the column names which we were just going over. And it's followed by a list of all the data. We can see that some of our data points are numbers, and some are strings, like the name of our planet over here, called Kepler-227b. Creative naming, I know. The key here is, because this is a comma-separated value file, all of these data points are separated by commas, and each row contains the data for a specific planet. Now, if we scroll down through this file, you can see that this file has thousands and thousands of different potential planets that were discovered by Kepler. In fact, if we scroll all the way to the bottom, we can see that there's over 9,000 of these potential planets. All right, now that we know what we're working with, let's get started exploring this data with Node. I'll see you in the next one.
Hey, it's me again. Just a quick update that in the next video, the latest version of the CSV parse package that Adam will show you has made a small change in how it exports the parse function, which means that we will need to replace this line of code below and instead pick out the parse function from the exported object by destructuring it like so. Everything else stays the same. That's it from me. Back over to you, Adam.
Welcome back. If our goal is to explore this question of whether we are alone in the universe, whether there's a possibility of life beyond Earth, and doing so by exploring the data that Kepler gathered by looking out into space, and using that data to find good candidates for humans or even alien life, we'd have to start somewhere. First, by reading in the data that we've downloaded. We could read our CSV file using the built-in file system module that comes with Node. But the file system module has no understanding of what CSV files are. When we read in a text file, it's just string data. Node will have no understanding that each line in our file contains a collection of data on a planet, or that each data point is separated by a comma. This is where our third-party modules in our NPM registry save the day. Let's do a package search for CSV and see what comes up. As is usual with Node, the ecosystem is rich. And so we have a few good options that we could go with. By far the most stable and most highly downloaded package that parses CSV files is this CSV parse package. That's the second result here in my list. It's really well documented, which we can see if we browse to the homepage. This means that it'll be easier for us to pick up exactly how to use the functionality it provides for us in our planet's project. And it provides a variety of different APIs depending on what we're most comfortable with and what exactly we're trying to do. If you learn these APIs, you should be comfortable working with any of the other available CSV packages. There's tons of pluses for working with this one, so let's get going and install it in our project. Now, remember, to use a package from NPM, we'll need to initialize our project in our terminal by using the npm init command. And this time we'll just be happy with the defaults. So we'll say -y to give us all of the default options. And now remember that the main file that we're specifying in our package.json is index.js. This is just the default name that Node gives to the main JavaScript file of our package. If you remember back to our discussion of index.js, we're not actually using any of the special behavior that Node has around this file. We're still keeping things really simple. So we can go ahead and create a file that matches that name. And before we write any code, we're going to install our handy little CSV-parse package. We'll run npm install CSV-parse. Now there's a lot of CSV packages, so make sure that it's CSV-parse and not parser or any variant like that. All right, so we have our package-lock.json and our package is installed in our Node modules folder, which means we can now start using it in our index.js, which would look something like const parse, and then assigning the module returned by the require function called on the CSV-parse package. There we go. let's dive right into what we can do with this package in the next video. See you then. Welcome back. What is streaming, and how do we deal with large data files in Node? That's what we're going to answer in this video. Looking at the introduction for our CSV parser, we can see that this package is a parser converting CSV input into arrays and objects, but most importantly, that it implements the Node.js Stream API, and that this provides alternative APIs for convenience, such as the Callback API and the Sync API. So there's various different APIs that we can use. Now, why does it do this? Why add all of this extra choice and complexity when it could just use one simple API? Let's look at the summary by clicking this API link. We can see that each of the APIs has their own advantages and disadvantages, even though under the hood, they're all based on the same fundamentals. Okay, so we've heard this streaming word thrown around, but what does this actually look like? Let's take a look. First of all, we see that this is the recommended approach if we need the most power, and that it ensures scalability by treating our data as a stream from the source to the destination. All right, that's a lot of buzzwords. And what does it actually mean for us? Well, the story starts with the way we get events through our CSV parser. Notice that when we require this module, we can then call the result as a function with these brackets or parentheses, and then we can call the .on function on the result of that. We've gone full circle all the way back to, that's right, the event emitter. In Node, all streams are implemented using the event emitter, where the events are emitted by Node, and we just react to the events on that stream using the on function. Now, why might we want our CSV package to use an event emitter? Say, instead of just returning all the data in our file all at once in a callback function, which we can see is actually an option. Well, let's think back to our data. That CSV file of ours had a whole lot of planets. Remember, it was over 9,000. This is quite a lot, but it's still likely to fit in our computer's memory. After all, each planet doesn't have so much data that it would overwhelm our modern computers. But what if we'd discovered millions of planets? The universe is vast, so this could very well be the case in our not-so-distant future. In order to be more scalable, that is, in order to support much larger data sets and to be able to work with them in a performant, efficient way, it makes sense for us to read in the data line by line, probably starting from the start of the file and not from the end. But doing this allows us to handle data as it comes in, as it's read from our hard drive, rather than waiting for all the data to be read before we do anything with it. This allows Node's event loop, in combination with our CPU and hard drive to all do their jobs as best as possible, so no one's waiting around needlessly. This is why we're going to be using the Stream API in combination with some of Node's built-in streaming capability. You see, many things in Node are streams, and we'll see this when we start working with HTTP servers and the web. We'll keep building up our knowledge and practicing this concept until we're really comfortable with it. For now, let's find some planets. On to the next video. Welcome back. We've learned that it's a good idea to stream large data sets, and that we're going to be using the streaming capabilities of Node to read in the data from Kepler. So let's apply what we've learned. We've seen that the return value from our CSV parse module is a function that we can call like so. And that function returns an event emitter that deals with streams of data coming in from that file. But the parse function doesn't deal with files directly. It only knows about streams, which is where Node's built-in file system module is going to help us do what we need to do. So let's go ahead and import it. But what file system functionality are we going to be using? Just like the file system module allows us to open a file and to read it as a string of text, it also provides a function called fs.createReadStream. This allows us to open the file as a readable stream. Let's find out what this means. We can see that our function takes in the name or path to the file that we're opening, and that it gives us back a readable stream. This readable stream is a kind of event emitter that emits various different named events depending on what's currently happening to that file. For example, the file was closed, or a piece or a chunk of data was read from that file. There's also events when there's no more data to be consumed from that stream. That is when we've reached the end of our file. And we also have one for if there was an error. Maybe our file doesn't exist. We can use these events to read our file in piece by piece. And every time a piece of data is received, we can do some processing on that data while we wait for the rest of the data to be read in. So for now, let's comment out this parse function and let's read our file by passing in the name of our Kepler data file to the function we just discovered, fs.createReadStream. This will give us an event emitter, which we can react to events from using the on function. And the most important function for us is going to be data coming in to our stream, which we'll receive in this data callback as a parameter to that callback function. With each chunk of data that comes in, let's create an array, which we'll call results, and we'll make it a constant, so we can't reassign the results, but we can update the contents by pushing values. So we'll push the data that comes in and store it in this results array. Now, when we reach the end of our data, let's just print the results that we've received. So we can actually call the on function again and do what's called chaining of different event handlers on our read stream over here. Because the on function returns the event emitter that it was called on, we can keep adding these .on handlers for different events that we might receive. So on the end event, we're not going to receive any data, but we will console.log our results array. And we can also just say that we are done processing our file. All right, now this should work, but let's be responsible and react to errors that might occur when we're reading our file. So for now, we'll respond to our error event, which gives us this error object in our callback function, just by printing that error. This might occur if, for example, the Kepler data file was misspelled. So let's actually test this out and say we try to load Kepler data with 3 A's. What happens if we try to run node index.js? We get our error being printed out that no file or directory called Kepler data was found. So it looks like our error handler is working. We've actually shown that the rest of our stream code is on the right path. So what happens if we pass in the right file name? Let me clear the console, and we get this array of these buffers. These buffers are just objects that Node uses to represent a collection of bytes, because our read stream is just reading the raw data in our file as bits and bytes. So we're reading in our file and all of our potential planets, but we still need to parse the results and understand the values of Kepler's observations. That's where the fun really begins. So let's get to it in the next video. Welcome back. We now have the data from Kepler being read in as a stream, but the results we get back are just raw buffers of bytes. What we really want is for each piece of data that comes in our stream, we want it to be parsed as a row of a comma-separated value file. For example, as an object where the name of our column is the key and the corresponding value is assigned to that key for each of our columns. That's the functionality that our CSV parse package gives us with the parse function it exports. So what's the best way of approaching this? How do we connect the parse function with the read stream for our file? Well, because the parse function is designed to be used with streams, like our readable stream, what we can do is pipe the output of our file to the parse function like so, by calling the .pipe function on the stream, passing in the result of the parse function. What this is doing is it's connecting the two streams together. The pipe function is meant to connect a readable stream source to a writable stream destination, a stream that takes in data as opposed to giving you data. So the Kepler file is our source, and the parse function is the destination for our pipe. What does this look like? We have our Kepler planets data CSV file. And we read that file as a stream by calling the createReadStream function and passing in the path to our CSV file. This stream here can then be piped to connect it to another stream, this time a stream that is taking in data and processing it somehow. This writable stream here is the result that we get from calling the parse function from our CSV library. And the result that we're hoping for is a series of processed rows that we can read easily to explore the data in our CSV file, which might take the form of an array of JavaScript objects. That's what we're hoping to get back from our parse function. So we have our read stream that's being piped to the parse write stream. This is always how our pipe function looks like. It's always a readable stream providing the input for a writable stream. The data coming in and the data being processed, flowing from left to right. So let's see this in action. After our Kepler data is passed to the parse function, the data we get back from this stream, from this event emitter, is now going to be the parsed data. But there's a few different ways of parsing CSV data. For example, the comments that we use can start with various different characters. It's up to whoever wrote the file. So for the file to be parsed correctly, we can pass in an option to our parse function by giving it this object and saying that the comment character is the hashtag symbol. So now we're telling it that we want to treat lines that start with this character as comments. And we're going to pass in one more option, which is columns being set to true. This will return each row in our CSV file as a JavaScript object with key value pairs rather than as just an array of the values in our row. Now, finally, when we run our program, we get an array of all of the objects representing all of the data that Kepler discovered, being streamed in from our Kepler data CSV file. And we can see that all 9,000 of our rows were read. We went from a stream of bytes to nicely parsed JavaScript objects just by piping the CSV-specific parsing with the file stream that Node already made available to us in the built-in module. Everything fits together really nicely. Awesome. Now that we've read in the data, we're ready to do some searching. Let's find some planets. I'll see you in the next one. Here we go. Let's find some Earth-like planets that might support life beyond our solar system. At a high level, we're looking for planets that are similar to Earth, orbiting stars that are similar to our sun. And so we're going to want to filter through all of these objects of interest that Kepler found. First things first, there's many objects in our list that haven't been confirmed. We're going to want to filter out objects depending on this disposition property, where disposition just means the current status of that planet. So it could be confirmed, but it could also be just a candidate or even a false positive. And so we're going to take the name of this column and going back to our index.js, let's create a function which filters out only those planets that are habitable. So we're going to call it isHabitablePlanet, and it's going to take in a object or a potential planet, and it will return true or false depending on certain criteria. The first of which will be whether that planet has a property called KOI disposition, which has the value confirmed. And when we receive the data from our stream, from our Kepler data file, we're only going to add it to our results list if that piece of data is a habitable planet. So now our results list is actually the list of habitable planets. Remember that the parsed CSV data is now coming back as a JavaScript object, which has a series of properties matching each column in our CSV file. All right, now on to the fun bit. A review of the best available research we have on habitable planets was done in 2015, and it showed that one of the factors that makes a planet habitable is the stellar flux, which is a measure of the amount of light that the planet gets, or in other words, the amount of energy it gets from its sun compared to Earth. So as an upper limit, the planet shouldn't get more than about 1.11 times the amount of light that Earth gets. Any higher, and the temperature of the planet would be so high that any water on its surface would disappear. It would evaporate in a very short period of time. And at lower values, we have a limit of about 0.36 times the amount of light that we get. Any lower, and the planet gets too little light, and the temperature gets far too low. This stellar flux could be the most important factor for the habitability of a planet. Without the energy from the star, life can't survive. So where can we find this data in our CSV file? If we scroll to the section just above the temperature, we can see this insolation flux property, which is a strange sounding name that's just another way of saying stellar flux. So then we're going to take this column name and filter on the value for each planet. So we're going to say the planet must be confirmed and its stellar flux must be greater than 0.36, and that same value must be less than the upper limit of 1.11. So just a little bit more light than we get here on Earth, and about 3 times less than we get. We're getting there. Next up, studies of the Kepler data have shown that there's an upper limit to how large a planet can be before it becomes more like Neptune than Earth. These large planets are almost entirely made up of gases and ice, rather than having rocky surfaces that we could build on, like Earth. And the upper limit for the size or radius of the planet is 1.6 times the radius of the Earth. Back in our CSV file, we can find that the planetary radius is represented by this property here, measured in Earth radii, which is exactly what we need. So let's add on a condition which checks that the planet's radius is less than 1.6 times that of Earth. And there we have it. We'll have some really great confidence on how habitable our planets are just from these few checks. We could always do more by narrowing down other criteria, like, for example, the star's temperature and how that compares to the amount of light that the planet gets. For now, let's run this scientific marvel of ours and see how many new Earth-like planets we've found. So when we've finished reading our data, let's add a log using our template string that says that the length of our array is the amount of habitable planets that were found. All right, let's see what happens. Our program has found 8 matching planets that might support life, and our search has only just begun. The hope is that one day we'll be able to travel to these planets and explore them from up close. Imagine that. This is very, very cool. All right, in the next video, we're going to examine the data from these 8 habitable planets. I'll see you soon. Welcome back. We've worked hard and done our research. We've gone down from nearly 10,000 objects of interest that Kepler discovered to 8 potential new Earths. So let's take a moment to explore what we've found and confirm that our results actually make sense. When we finish processing our data, we could just print out the entire contents of our habitable planets. But if we run this, we can see that our data includes a lot of properties that we're not really looking at. So instead, let's look at the names of the planets that we found and use that to confirm that our program is working by comparing it with the results that other scientists have come up with. We'll do this by mapping over our habitable planets array. This map function takes a callback that for each item in that array processes it somehow and returns a new value for that item. So we're going to use this to take our planets object that represents one item in our list here, and we're just going to return that object's Kepler underscore name, which corresponds to the name of our planet. So we're basically just filtering out or selecting the Kepler name property from each of our planets. And let's see what we get. Oops, I'm getting a reference error, so I must have mistyped the name of our parameter here. So it should just be planet, representing one item. That makes sense. And let's try it again. There we go. The names of our planets are Kepler-1652b, and so on and so on. But do these results actually make sense? The Habitable Exoplanets Catalog is a widely referenced source on habitable exoplanets. And they maintain this list here, which includes observations not just from Kepler, but from other telescopes as well. And you can see here at the bottom that they have 5 Kepler planets listed. Do their planets match ours? Well, let's see. Well, we have Kepler 442b and 62f, which I see are the last 2 listed in our catalog. So we're definitely on the right track. The results listed here are slightly different than ours because the exoplanets catalog is not updated as frequently as our data. And it also uses slightly different criteria than we did. However, our understanding of the observations made by Kepler and other Earth-based telescopes is improving day by day, and new observations are being made as well. If we scroll down on this page to the more optimistic sample of potentially habitable exoplanets, you'll see all of the planets that we've found and more. Our Node application actually narrows things down more than this official list. We've come quite far just by looking at the available research and the Kepler data that's fully publicly available. I'll leave you with just one thing. If you look at our list of planets, one of the results that we see as one of the better candidates for an Earth-like planet was Kepler 442b, which we can see in our catalog as well. Given what we know, this planet might look something like this in comparison with Earth, which we have here on the right. This exoplanet is sometimes called super habitable because it might be more habitable than Earth. That is, it might have conditions that are better suited for life to thrive than those that we have here on Earth. That red color that you see in this depiction of the planet isn't necessarily rock, but actually plants and other vegetation on the surface of that planet. This idea is something that really caught me by surprise, so I thought I'd share it with you. All right. I promise we'll get back to Node now. But I hope you're as fascinated by all of this as I am. We can do real research on our universe in much the same way that we're doing right now. As an exercise, see if you can play around with our criteria here by looking at other research and maybe duplicate or improve upon the results that we've found. And on that note, I'll see you in the next video. Bye-bye.
Damn, I have to say I'm pretty impressed. It's no secret that this crash course is a long one. In fact, about 96% of people who started this crash course didn't make it, but you did, so give yourself a pat on the back for that. Go for it, do it right now, I'll wait. But don't get too carried away. You do now have the fundamentals of Node.js, but there's still lots to learn. The good news is you have what it takes to become a professional backend developer in the industry. But if you truly want to master Node.js and become a top 10% Node.js developer, you have to keep learning. And what's the best way to do that? You guessed it, take the rest of Adam's complete Node.js Bootcamp course. I mean, you just finished about 6 hours of the course, so you know how great the rest is going to be. This crash course only included 2 of 13 major sections in his full bootcamp. And there's still tons of topics that you're gonna get to learn that 95% of Node courses don't even cover. So you'll be miles ahead of anyone learning Node. So go click on the link in the description below and sign up for Zero to Mastery and keep that momentum going. Oh, and there's also a special discount code there for you guys. You're welcome. Last thing, I'm not sure why we even need to, but if you want to see everything else that's included in the rest of the course, click on the video right there on your screen. But be careful because your mind will be blown. Okay, one more final thing. Can we please show Adam some love in the comments below for sharing this amazing resource with us? That's it for now, and until next time.